folks. Now we're getting on to chapter 11. This is going to be your properties of solutions. If you remember back to previous semester, you'll realize that this is actually a direct extension off of where we first started talking about solutions. Things like molarity are going to start showing up again. We'll do some recapping of that, but if you need to, you may want to look back in your book, back to the original chapters on solutions, which usually are like chapters 3, 4-ish, depending on the book. Now, this is going to be where you have mixed two different things. So you remember that we had different types of pure substances, different types of mixtures. This is going to be one of the types of mixtures. These are always homogeneous mixtures or homogeneous, depending on what country you originate from. And that means that you can't see one part from the other. And table of contents, of course. Right here's the various types of solutions that you'll see. And so, for example, we have a gas mixing with a gas. So a gas is our solution, our solvent, and our solute is another gas. Actually, for the air that's around us, typically this is going to be nitrogen, and this would be like oxygen or one of those other components. This then is going to give you a gas overall, and that's the stuff we're breathing in right now. And so that's our air that we're dealing with right now. Right here we see a liquid mixing with another liquid. These are actually different types of alcohols mixing with a water as the solvent. And that gives you a liquid overall. Right here we have brass. This is actually two different types of solids mixing together. And that will give you a solid overall. And you see the various different mixtures you can get and examples of them. So, as a solution goes, as a mixture, so one of the most important things you need to understand about it is its composition. And so mixtures do have a variable composition. They're not all one thing, and they can have, you could have vodka or you could have beer, right? And those are two different types of mixtures that have different compositions, but mostly the same substances in them, which is alcohol or ethanol and water. Now, the amounts of the substance solution, we need to specify those because it makes a very big difference whether we have, for example, lightly salted drink, like a soda or something, or if we have brackish seawater. It also makes a very large difference whether we had beer or vodka, right? Especially if we end up in the emergency room. So, we can do this in two different ways. We have the qualitative terms, dilute and concentrate. For example, when I said the word brackish, that was actually an indicator that this was a concentrated solution of salt water. Whereas where I said like a soda dilute solution, that is a dilute solution of salt and water. Those are qualitative. The quantitative terms are going to actually have quite a variety. And that is because there is, of course, a great number of solutions that have been made throughout history. Various types of quantifications have been made to explore those solutions. And some of them just work better in certain situations. For example, we have molarity, which is big M. Molarity works great in labs because it's the number of moles of a solute per liter of the solution. Notice this is the solution total. That's everything mixed into the solution. So this works great in labs because moles is fairly easy to find of a solute if you mix this. And that's because you can just put it on the balance. You can use your periodic table to go grams to moles. And then you can just pour everything into a graduated cylinder or similar device and get the amount of liters. And so figuring out molarity in labs is very, very easy, very quick, very useful. However, it is not like that when you're on a factory floor and you're trying to make 20 million cans of Coca-Cola. That molarity would not be a good measurement of your concentrations for Coca-Cola or something similar. So, Molarity, very useful in labs, very useful in scientific context, usually. Mass percentage is usually what you see for things like alcohols. That's what you usually see. You either see a mass percent, which is weight percent, or you see a percent by volume whenever you look at something like vodka, beer, rum, wines, that sort of stuff. This is a fairly common way you would market things as, because it's much easier just to weigh everything out. So I mix together, 10 tons of this with 1 ton of that. What is my ratio? Well, it's 1 to 10, right? Or I have 1 of this divided by 11 of the mass total. You will notice in mass percent, this mass and this mass, these don't have units. They just have masses. That's because you can put anything here. You could put a gram and a gram here. You could put a kilogram and a kilogram here. Or like my example, you could put a ton and ton here. And these will cancel out, leaving you with percentage, right? And so again, it's just going to be your mass of your solute, that's the one that's in less quantity, divided by the mass of the solution. So again, the solution means the whole thing. And of course, like every other percentage, this is always in amounts of 100, right? I'll show you another unit. I want you to keep in mind that this is times 100, and then percent is actually your unit designator, okay? That's your symbol for this unit, that it's parts per hundred, if you will, that you're looking at here, which we usually call percentage. Now, mole fraction, the only place that I can remember that you've typically seen mole fraction is you typically see this whenever you're looking at something like the composition of the atmosphere. In fact, those percentages we've mentioned before, last semester usually, for the composition of the atmosphere, where you have 71% of it is nitrogen, 29% oxygen, etc., etc. Those are actually in mole fractions. Those are not actually percent by weights like you probably thought. So really what you've actually been saying all that time was it was 0.71 mole fraction. It was 0.29 mole fraction. And it just, people use it as percentage because it's easier than telling people what mole fraction is. This right here is chi. This mole fraction, it's literally going to be what it says. It's going to be the fraction of your mixture that is the moles you're talking about, or that species, right? And so the mole fraction of component A would be represented like this. You'd have chi sub A, and that's right there is denoting what species it is. This would be like chi CO2, chi O2, chi N2. And then this is equal to the species that you've designated right here, the number of moles, divided by the total number of moles here. In this case, this is only 2 species, and so you only have 2 things here. All right, now, this right here is molality, not to be confused with molarity. Be very, very specific, very careful, okay? Molality is a very different quantity than molarity. They're related, but they are different. Molality has a designator of a small m, is its abbreviation. This is one of the reasons you always have to be very, very, very careful. Whenever you're doing molarity, you need to put a big M. Molality is a small m, and I see a lot of students get confused about this and forget this on exams and everything else. They'll give me answers that are molarity, where we're talking about molality, that's what was asked for. Or they'll do the opposite and write small m, and that's, they meant big M, and they just blanked out. And that happens a lot. So again, that's why I stress this and spent, 5 minutes just re-going over it and kicking a dead horse, if you will. Okay, so this is going to be your moles of solute divided by your kilograms of solvent. Notice the moles of solute is the same as molarity, but the bottom is very different. Everything about the bottom is different. This is kilograms, which is a mass, of your solvent only, not your solution. Notice that's different than these other ones. This is just the solvent. This is literally just the mass of the solvent that you would say pour in. This is actually very useful for some very specific purposes, which we'll see later, and we'll actually do a few examples of. But you need to understand the basic concept of molality. Okay? Alright, so a solution is prepared. Oh, one thing I want to mention here before we go on. This moles of solute for kilograms of solvent, and this right here, moles of solution over liters of solution. For water, if you have very dilute solutions of water, those two concepts end up being essentially the same thing. And the reason for that is that if you have a very dilute solution of water, so it's almost all water and very little solute, that means the mass of the solute is almost negligible. You can ignore it. Whereas the liters of solution, well, what is the density of water? It's 1, isn't it? And so your liters of your water would be essentially the kilograms of your water as well. And so very dilute solutions, you want to keep that in mind. The molality and the molarity will be almost the same. They'll be very, very similar. So a solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Let's calculate the molarity, mass percent, mole fraction, and molality of the ethanol in this solution that is solute ethanol, solvent, water. Okay, so notice they've given you a final volume here. You have the grams of the water, which is your solvent, and you have your grams of your ethanol. So the first thing we need to do is we need to get a molarity. When we do molarity, well, what is molarity? I have a little bit of a funny story with molarity that will hopefully make you remember this. I won't be able to actually follow through on my promise on it because yelling into the camera just doesn't really work. So, when I went through this as an undergraduate, I did this alongside one of my very good friends in undergraduate university, and he had a hell of a time remembering molarity. He just had a mental block and found it to be incredibly difficult to do and kept missing questions on the exams. So finally, we're studying at like 3, 4 in the morning one night, and we're both really hyped up on cocoa coffee. Try it sometime. It's what I really used to like when I was studying a lot. You essentially make cocoa using coffee. And we're studying at the top of the 5th floor of our science building. It was a pretty good sized science building. And he, for the 20th time that night, goes, what is molarity? And so I look up at him, I hit my hand on the desk and yell, moles over liters! I yell this so loud, and I have a hell of a pipes on me. I actually had the security guards that had been patrolling outside the building come up to see if everything was okay on the 5th floor of this fairly large building. So, and the funny part is not that. The funny part is that like 5, 6 years later, he had gotten married. I was one of the people that was part of his wedding party. And he's sleeping with his wife. And he wakes up and is yelling, it's moles over liter! And his wife goes, what the hell? And he goes, he had to tell her this story of me apparently scarring moles over liters is molarity into his mind. So if you have troubles with this, get somebody to yell it really, really loud at you. That's moles over liters, okay? Ah, man. Anyways. So, molarity is moles over liters. We have grams. Well, we know grams can get to moles by using the molar mass of this formula right here. And so we look up these on the periodic table. We add together each of them to get our grams per mole, which is a molar mass. And then we will get moles from that. Then we can use the final volume here, but we need that in liters. So let's go and do it. Right here, this is the molar mass of ethanol. And so we're going to take that grams of ethanol right there. We're going to use its molar mass. Remember how to do this is you always get, this is grams. You have to then divide by grams. So this grams part right here goes on the bottom. This right here, which is always 1 before it in the denominator, is on top. So that will be 1 mole. And these grams will cancel, leaving us in moles, which is right there. And so that is our moles of ethanol. We have half of the molarity problem. By the way, you'll be able to recycle those later for some of the others. Now, our volume, we have 101 milliliters. How do we get that into liters? Well, there's 1,000 milliliters per liter. And so 1,000 milliliters is on the bottom to cancel out milliliters, and 1 liter on top to give us liters. And that leaves us at 0.101 liters. So we then are going to take our moles, divide it by our liters. So we take our moles number and divide it by our number in liters. There we go. Congratulations, that will give you your answer, which is 0.215 molarity. All right, so mass percent. Remember, this is just a percent that we express in mass. So we literally just have to take the mass of our solute, which is ethanol, and divide it by the total mass of our solution. And so we have 1 grams of ethanol. Now, our total mass is going to be the 100 grams of H2O plus the 1 gram right there of the ethanol. And so this will give us 1 divided by 101. And then we need to multiply it by 100% to get an percentage. And that's 0.99% right there. Or just a little bit below 1%, right? I hope none of you are particularly surprised about that. All right. So the next thing we're going to do is we're going to do mole fraction. So again, we need these in moles now. So we already have the moles of ethanol. We figured that out before. But we need the moles of water. And so what we're going to do is we're going to take that mass of water and we're going to take its molar mass, which is the oxygen plus 2 hydrogens off the periodic table. That's in grams per mole, so grams needs to go on the bottom, moles on top, and that gives us 5.56 moles. So we go ahead and put all our numbers in, moles of ethanol, over the moles of ethanol plus the moles of the water on the bottom. And that will give us our answer right there, which is 0.00389. By the way, chi can never be above 1. I hope you would all realize that chi can never be above 1 because you literally total everything in the bottom here, the denominator. Above 1 would mean you have more than 100% mass. You have more than 100% of what you started with. You've created molecules. Molarity. So molality is going to be moles of our ethanol over kilograms of our water. So again, we use that moles of ethanol number that we figured out before. On the bottom, we're going to have to take the 100 grams of water. We're going to have to go, well, there's 1,000 grams in a kilogram. And so there will be 1/1000th of 100, which is 0.1. So we have our moles over 0.1 kilograms of our water. And that will give us 0.217 molality, which is small now. Okay, excellent. Make sure you try those and get those really down, okay? You need to understand those to go on to understand anything else in this chapter, and those will be repeated concepts that will show up for the rest of your lives in a science career. Literally, you will never get rid of the percent by masses, parts per million, parts per billion, which I'll show you later, molarity and molality. Those will always go with you. So critical thinking, you're given two aqueous solutions with different ionic solutes. So we have solution A, we have solution B. What if you're told that solution A has a greater concentration than solution B by mass percent? But solution B has a greater concentration than solution A in terms of molality. Is this possible? If not, explain why. If it is possible, provide example solutes for A and B and justify your answers with calculations. Okay, folks, sorry I had to go get a drink. So I don't remember where I was, but I believe I talked about the question, and in which case I'm going to talk about the answer now. If I forgot, please let me know. Okay, so you have solution A and B, right? And what we're really looking at is what's the difference between a mass percent and a molality. Well, your big difference is, remember, your mass percent and your molalities both have denominators that are masses, right? But in this case right here, it's the total mass of the solution, and here it's going to be the mass of the solvent. Okay, now what else are you looking at? Well, in molality, it's moles of solute over the mass of the solvent. In mass percent, it's going to be the mass of the solute over the total mass of the solution. And so, let's see, we have moles here in the numerator, we have mass in the numerator here. Well, that leads to a fairly large difference, doesn't it? Because you have things that have, if you look on your periodic table, you have things that have large molar masses and you have things that have small molar masses. So let's think about that. If we had a very large molar mass, okay, then, and let's say you had 1 mole here in your molality, well, that could give you like a 200 grams in your numerator in the mass percent, couldn't it? Because some of the stuff we've calculated has well above 200 grams per mole. Now, on the other hand, you could have something very light. You could have something that 1 mole of it would only give you something like 10 or 15 grams, right? And so, yes, there can be a very, very large difference in this, right? And it's all going to be based on what is its molar mass. If it has a very high, large molar mass, then your mass percentage is going to be very large, but your molality would be very small. And so when we look at examples, there's a lot of examples this could be, okay? There is hundreds of examples you could give that would give you these terms. But what you're looking at is the difference between something that's like FeCl3, which would be fairly heavy for its number of moles, it has a larger molar mass, versus something like sodium chloride, which has a much smaller molar mass. Or you can even go smaller than that. This could even be something like a solution with lithium chloride, or even worse, it would be something like lithium fluoride, which is extremely small molar mass. Essentially, the closer to the top of the periodic table you get things, the smaller their molar masses, right? The closer to the bottom you get things, the larger their molar masses. So you would have a really huge example of this if you go down to something like uranium, making a ionic compound of salt. All right, so normality. Now, we talked about molarity, and that's a very commonly used concentration when you're talking about laboratory settings to measure these concentrations. Now, normality is going to be related to molarity, okay? It is related to molarity in that the only real difference between them is that when you talk about normality instead of moles, you'll have what's called equivalence, okay? And so I'm going to give you these definitions, and then we'll go back to comparing them and understanding the normality more. Just remember, it's like molarity, like a measure of concentration, but it's going to be the number of equivalents. You can shorten that to EQ, by the way, per liter of solution. And keep in mind, if you're blanking out, per means divided by liters of solution. Now, the definition of equivalent is actually going to depend on your reaction. The easiest way to think about equivalence is when you have a reaction, you have HCl plus NaOH gives you NaCl and water, right? That's the basic neutralization reaction you have seen before, and you may remember from previous examples. Now, those could be, you could be reacting one molecule of each. You could also react 1 mole of each. You could react 10 moles of each. It doesn't really matter exactly how much you react, right? You always have equivalence, which means that if you react 1 mole of reactant A, or HCl in this case, and you would have to react it with 1 mole of NaOH, right, to get the reaction to go to completion. Now, if you had 10 moles, you would have to have 10 moles of the NaOH as well, right? And so they are one equivalent, reacts one equivalent of the NaOH. All right. So for acid-base reactions, the equivalent is going to be the mass of the acid or base that can accept or provide exactly 1 mole of protons. And so what you're talking about when you talk about normality or equivalence when you're talking about acid-base reactions is each normality will be 1 mole of the protons. So a monoprotic acid, which has 1 H plus coming off of each of the acid molecules, so for example HCl, that would be a 1-to-1 ratio. So literally in HCl, or a monoprotic acid, 1 mole of it would give you 1 mole of protons. And so the normalities for HCl are the exact same as the molarities. There's no difference. All right, now, what if you had something that could give you a diprotic acid? That would be 2 moles of protons are given for every mole of the diprotic acid, such as H2SO4, or sulfuric acid. So I didn't have enough water. Well, in that case, your molarity could be 1, right? Whereas your normality would be twice that, and so 2. So in the case of something like a diprotic acid, your normality would be twice your molarity. And that's because each mole of the acid gives you 2 moles of protons. Triprotic acid, it would be 3 times. So the normality would be 3 times what the molarity would be, and so on. So for an oxidation reduction reaction, your equivalent is the quantity of the oxidizing or reducing agent that can accept or provide 1 mole of electrons. So when you look at an oxidation reduction reaction, what you're counting is the number of electrons that are going to be provided from each side. That's what causes the reaction. And so when you're looking at these, you would have to count up the number of moles of electrons that would be provided. For example, if you had a reducing agent and it gave you 1 mole of electrons for every mole of the reducing agent, these numbers would be 1-to-1. So for every molarity, you would have 1 normality. If you had something that could give you 2 electrons, then this would be 2 times. And so for every molarity, you would have 2 normality. What am I talking about examples-wise? Well, it's like lithium would give you 1 electron. So lithium would normally only lose 1 electron, and that would be something that would be a 1-to-1 ratio. 1 molarity would be 1 normality. There you go. Something like iron, for example, could give you 3 electrons, and so you would then be a 3 moles of electrons for every mole of the molarity of the reducing agent. So 3 normality for every molarity. All right, so let's try this out. The electrolyte in automobile lead storage batteries is 3.75 molarity sulfuric acid solution that has a density of 1.230 grams per milliliter. Calculate the mass percent, molarity, and normality of the sulfuric acid. And so one of the things, excuse me, I keep having trouble pronouncing things. Let me get a drink of water real quick. Better. So sulfuric acid. So one of the things you need to remember is oftentimes in these interactive examples, I will take the opportunity to review past material in this chapter and brush up on your fundamentals, and then we'll actually do the real problem, which is normality here. And so we're doing mass percent, molality, and normality of sulfuric acid. We have these, which is 3.75 molarity, and the density of the solution. And so, what is the density of solution in grams per liter? Is the first thing we need to figure out. We have it in grams per milliliter, but we have a quantity here that is in liters. And everything else is always in liters, right? And so we go ahead and convert that. So the mass will be present in 1 liter. Well, how many milliliters is in a liter? There's 1,000 milliliters in a liter. So if you had 1 liter of the solution, you just need to take that density, multiply it by how many milliliters there is in a liter, which is 1,000. And so we take 1,000 times our density number, which is 1.23 grams per milliliter up here, and we get our number in grams per liter as so, which is 1,230 grams per liter. By the way, if you want to do it in a nice mathematical format, again, you can always put 1.23 grams divided by 1 milliliter. Multiply it by, you need milliliters on top to cancel, and you need liters on bottom. There you go. So we have 3.75 molarity. That means that there are 3.75 moles for 1 liter of the solution. So if you have a liter of the solution, of this solution of sulfuric acid, then that means that you will have 3.75 moles of the H2SO4. The number of grams of H2SO4 present would be, well, we again have moles. And so 3.75 moles, which we figured out here, times the molar mass that we get off the periodic table for H2SO4. And so we just add these from the periodic table to give us our molar mass. Again, grams needs to be on top, moles needs to be on the bottom because moles must cancel out. And that leaves us with 368 grams of H2SO4 in our solution if it was 1 liter. By the way, whenever you do percentage problems, which is ultimately what we're actually trying to do right here, it's best if you just assume a number that would either be 1 or 100. So you can then work with real numbers instead of trying to figure out percentages. All right. So how much water would be present in this 1 liter of solution? Well, the amount of water present in 1 liter is going to be obtained from our differences in the masses, like so. So we have our mass of our solution, we subtract it with the mass of the other stuff, which is sulfuric acid, and we'll be left with the mass of the solvent or the water, right? And that gives us 862 grams of H2O. So next thing we can do is we have everything we need for mass percent. And we actually have set up everything we need for all the rest of the problem. All right, so what is the mass percent? Well, we know the masses of the solute, we know the masses of the solvent. And so we can calculate our mass percent. So we take our mass of our solute. For the mass percent, we divide it by the mass of the total solution, right there. and then we will multiply it by 100%. And that will give us 29.9% H2SO4. So what is the molality then? Well, the molality is moles of solute over the mass of the solvent. That's what we actually needed, by the way, this number right here. You will notice we did not need this for the mass percent. All right, so we're going to take our moles of H2SO4, which again we've already figured out. We're going to divide it by our mass of the water, which is the solvent, but we need that in kilograms. So we have our moles right here. That's 3.75 moles of H2SO4 that we got for a liter. And again, we're doing it all for 1 liter of this solution, so we can simplify these numbers and make them easier. And when we did that for 1 liter, we got that the difference gave us 862 grams of water for this 1 liter solution. But we need that in kilograms, so we're going to divide it by 1,000. So we then do the math, and we get 4.35 molalities, mol. So what will be the normality? All right, so the next thing we need to do is we need to figure out how many equivalents there are, and we're going to then have to do the normality, which is much like molarity. Notice the similarity in the names, by the way. So since each sulfuric acid molecule can give you 2 protons, how do I figure out this can give me 2 protons? Well, there's 2 ways. I could remember this from the previous chapter where we talked about acids and bases. The other way is I could look down here and realize that this has 2 protons on an anion, which is SO4. And that means that these are acidic protons. We can lose those, much like an ionic compound. And so I know then I can donate up to 2 because there's a 2 there. That's it. Now, that means that 1 mole of this compound represents 2 equivalents. And so, a solution with 3.75 moles of the H2SO4 would give you 2 times that number of equivalents in a liter. So again, remember this is the moles that were for 1 liter. 2 times that number would give you 7.5 equivalents in a liter. Notice that we don't need to indicate the acid H2SO4 anymore because we have equivalents. These are what are actually going to be reacting with things. We don't actually care what the specific acid would be anymore. The normality thus would be 7.5 moles divided by, or equivalents in this case, divided by the number of liters, which is 1. And so that gives us 7.5 normality, which is capital N, very similar to the molarities again. So in a 0.1 molar solution of NaCl in water, which one of the following will be closest to 0.1? And so which one of these would be the most similar? Now 0.1, that's fairly small numbers, so that means it's fairly dilute solution. And so one of the things I had pointed out to you is that if you have a very dilute solution in water, the molarity is going to be very similar to the molality. And so is the molality of your NaCl is going to be the most similar. And that's again because the density of water is 1. If the density of your solution is close to that of water because it's very dilute, then yes, it will be very, very similar numbers. All right, so what are the steps involved in the formation of a liquid solution? On the molecular level, we need to understand these steps so we can better understand these solutions. 1, we need to expand the solute. So the solute is going to be separated into its individual components. Say if we have NaCl, the sodium is going to break apart from the chloride, and that's how they will dissolve. So we will expand those solutes. If we had water, we are going to have the water molecules that make hydrogen bonding. Those hydrogen bonds will have to be broken, and then say you're diluting it with ethanol. Well, then ethanol is going to have to slot in between and bind to that water molecule. through hydrogen bonding. And so you first always have to break to then reassemble. And this is breaking the solute or expanding the solute. The second step is going to be that you have to expand the solvent. First off, this should have been kind of obvious to you because you're slotting the solute into the solvent. So if you put your finger into water, you're breaking hydrogen bonds all the way through until you stop putting your finger further in. And that's literally how you expand the solvent, right? You're actually expanding the surface area of the solvent to encompass your finger. And so you're expanding the solvent in that case. If you throw salt crystals in to go into the solvent, to insert, literally go physically into it, it has to expand the solvent and break those hydrogen bonds. Now, when they start interacting with the solvent, so your solute and solvent start interacting, they have to be separated from each other. So the solute has to be separated from other solute molecules so it can interact with the solvent. The solvent also has to be separated. It has to have its hydrogen bonds or dipole-dipole interactions or London dispersion forces, whatever it has, broken so that it can form new interactions with the solute. And so the first thing you do, steps 1 and 2, those are going to take energy because you have to break these interactions that already exist so you can reassemble. Step 3 is going to be the step where you allow the solute and solvent to interact, and these will form your solution. Okay? So steps 1 and 2, these take up energy. They're endothermic steps. They're always endothermic steps because you always have to break any interactions that are there. Much like if you try to move a magnet or put something under a magnet, well, first you have to break the force of the magnet, right? And that takes energy. So that's endothermic. Energy is being put in to the solute and solvent, or to your system in this case. So these forces must overcome and to expand the solute and solvent. This actually tells you a lot of information right here if you start thinking about the implications. For example, if I don't stir something, this is going to take a very long time, right? Because I'm not providing energy to break those interactions. I'm not providing energy to overcome that as easily. Or for example, the faster this will happen much faster if I were to heat the solution. So if I want to dissolve salt in water very quickly, or I want to make a solution, I would want it to be warmer, right? Because that will help me make it faster because I have more energy to overcome these bonds or these interactions. Step 3. Step 3 is the step that's oftentimes exothermic, but it doesn't have to be either, actually. So if your solution tends to be made, if your solution is spontaneously made, this is typically exothermic. There actually is another factor that can make it spontaneous, but we're not going to get into that this chapter, okay? That's going to be when we talk about, well, thermodynamics more. And you already touched on thermodynamics last semester, but we'll go a little bit more in depth later. But typically, if this solution is going to be made spontaneously, where it happens on its own, like when you throw salt crystals in water, it'll spontaneously dissolve and make the solution, right? You throw sugar in water, it spontaneously dissolves and makes the solution. Step 3 in those cases is typically exothermic, where you bind the salt, NaCl, the sodiums and chlorides, to the water molecules using ion dipole interactions. That's exothermic, that gives off energy. In the case of sugar, it would be hydrogen bonding, so you're making hydrogen bonds. That will give off energy, that is exothermic. By the way, sometimes step 3 can be extremely exothermic, and that is where you would literally, if you mix this solution, it'll be hot, okay? And so if anybody's ever let you touch something like HCl after they mix the concentrated solution or some other things, the hot packets have a similar sort of thing going on, where it's an exothermic reaction when they mix. Um, yes, that's what we're talking about. By the way, the cold packs that you break the seal and they get cold is actually a solution being made. And that solution actually has a step 3 that is also endothermic. And that's why it sucks up energy and makes it cold. So the enthalpy heat of a solution is the delta H solution. That is the symbol for it. This enthalpy change that's associated with the formation of the solution is going to be the sum of these delta H values for the steps. So it is the delta H of step 1, the delta H of step 2, and the delta H of step 3 added together, summed together, to give you the total delta H change in enthalpy of that solution. The delta H solution can have a positive sign when it is absorbing energy and is endothermic overall. It would have a negative sign when energy is released, which would mean an exothermic overall. Typically, what you will see is these two right here will be positive. This one will be negative. All right, so right here is an example graphically. We again have lower energy at the bottom, higher energy at top, just like a building. So if you fall off the first floor, it doesn't hurt very much. If you fall off the 10th floor, it's going to hurt a lot. All right, so right here we have our energies of our separated solute and solvent. These are, you have salt, you have water, they haven't mixed together. So when you throw them together, the first thing that's going to happen is the salt molecule or atoms, ions, have to be broken apart. The water molecules have to be broken apart. And so that's step 1 and 2, which is this energy that's getting used up right here, making that system higher energy. The next thing that's going to happen is you're going to start having ion dipole interactions. The sodium start attaching to the water molecules. The water molecules start attaching to the chlorides as well. And that's going to give you step 3 right here, which is, in this case, exothermic. And so in this case, your total delta H of your solution is actually exothermic. It gives off energy overall, which is the difference between these two right here. Now, this is the other case. In this case right here, again, we've used up energy. It's endothermic when we break apart the solute and solvents, steps 1 and 2. In step 3, this had a very small exothermic energy release. Didn't release a lot of energy. And so your overall delta H of solution is actually endothermic. You see that? And it still takes up energy overall to make this solution. And you would feel it cooling your hand in this case. In this case, it would release heat onto your hand and feel warm. All right, so what are some of the factors that favor a process? Well, the increase of probability of the mixed state when the solute and solvent are placed together. Processes that require large amounts of energy tend not to occur because you won't be able to overcome the energy of activation or activation energy. One of the things you can think of is, why does my car not just spontaneously explode? Well, it can't, it doesn't have the activation energy. But if somebody were to put a lit flame into my gas tank, that would provide the activation energy and that would cause my car to explode. If you put salt into water, if it's cold enough, they're not going to mix, okay? Because you just aren't going to be able to overcome the activation energy. Like dissolves like. Actually, the like dissolves like is actually right here. That's what we're looking at here. So this like dissolves like is actually telling you the strength of the interactions between the solute and solvent, right? That strength of the interactions is an energy value. So the stronger those interactions, the lower energy they are. The more energy that would be released by making them. The weaker the interactions, the less energy that's released by making them. And so here you see something that's like dissolves like. Here you see something that is not similar enough. They're not releasing enough energy. These interactions are not strong enough. Okay. So right here, we see some different examples of a polar solute, polar solvent, and we see that these energies for breaking apart are large, but so is the energy when they combine. And so our overall delta H solution is, they're very similar, so that you have a very small overall delta H solution. And so typically this solution would form. It doesn't have a huge energetic drive for it. You may not be able to feel it's heating up or cooling down, but it'll typically happen because the energy difference is very small. And energy is all around you, right? Especially when it's hot out like this. All right, nonpolar solute and polar solvent. This is going to have the delta H for breaking apart the nonpolar solutes is fairly small. The delta H for breaking apart the polar solvents is fairly large. So the delta H for them combining is going to be fairly small. Well, what that means overall is that breaking them apart is going to be very hard to do. And they won't typically combine because you have a large positive delta H solution due to this large amount of energy that would be required for breaking the polar solvent apart. And that's why nonpolar and polar typically do not mix. Nonpolars, everything's going to be small. So if you put nonpolar solute with nonpolar solvent, everything's small. Doesn't take very much energy to break apart either, but you also don't get much energy out of it. And so the solution typically forms. There you go. Polar solute and nonpolar solvent, you just exchange which one of these is small and large from previously. So again, your polar solute has a large delta H, break that apart. In the nonpolar solvent that has a small delta H, break it apart. You don't get much delta H back because they don't interact a lot. Remember, your polar solute and nonpolar solvent, they're not going to make polar interactions. They're going to make London dispersion forces, not hydrogen bonding. Okay? This is again going to be large positive delta H solution, which would mean that it's going to be very, very hard to form the solution. You would need to continuously provide it a large amount of energy to even hope to have a solution form. And the second you stop providing it large amounts of energy, it will start separating again because it's spontaneous for them to be separated. By the way, that is why if you take gasoline, oil, and mix it with water and just keep mixing with a little bit of heat usually, you can actually get them to mix temporarily. But they will separate on their own. So, thin layer chromatography, TLC. This is actually going to be something that will use these properties that we've discussed just now in a physical setting to be able to test substances. This is actually how they originally, they still do something very similar to this to test DNA patterns. Like say you have a crime scene and you get the person's DNA off the victim, and then you start matching it to DNA samples. This is how you would do it. This is how they used to do it, and they still sometimes do it this way. It's the easier, faster way to do it, and it works very well. This can also be used to say, you guys may have heard of the Unabomber. One of the ways they caught him is they tested the inks from his letter, and as it turns out, the ink that he used was not a particularly widespread brand of it, and they were able to narrow it down and finally find him. And so you can do this with ink as well. You may have noticed that when you have ink from your pen on your paper, if it gets certain things spilled on it, like if you happen to spill water on some inks, they'll separate a lot. And if you happen to spill water on other inks, they'll separate very little. And that's because the components of the ink, some of them are very polar, in which case those polar components are going to separate a lot, right? When you spill water on them. The ones that have not non-polar components in them and not a lot of polar components in them will not separate much. The components will individually be different, whether they're more polar or less polar. And that's why you get that sort of almost rainbow pattern coming off of these inks, especially if you have black ink. Black ink is actually a mixture of essentially the extras that that company has of all the other colors they make. So they dump all the extras into black ink to bulk it up. And that's why if you spill water on it, or depending on the pen, if you spill like vodka on it, you can try this at home, you will see that the colors will run more or less, and you'll get the different colors different places. And you're literally doing TLC there, thin layer chromatography. That is what that is. So the TLC plate, this typically consists of a plastic sheet, which is then covered with a thin layer of silica gel. This does not actually have to use a TLC plate. They're just the most common way to do it. There are a wide variety of different media you can use for TLC. This is just a technique. So the silica gel is very polar. It's capable of hydrogen bonding. And so things you get that are very polar are going to tend to attach to the silica gel, and when you have things trying to spread over it, those polar things are not going to spread much because they will attach to the silica gel very tightly. Things that are non-polar are going to spread much more easily because they do not attach to the silica gel as well. So the mixture to be analyzed would then, you would take your plate, you would dot it on one end of that plate so that the mixture to be analyzed would be dotted on that end of the plate, one end of the plate. That end of the plate would then be dipped into a solvent. That solvent is referred to as the mobile phase because this solvent is going to travel up the plate due to capillary action. Think about when you have a glass of water, if you dip a towel or a paper towel into it, loop it over the other side, you will see the water slowly move up the towel, right? Well, this is the same thing. So if you dip this TLC plate into your mobile phase, it will slowly move up the plate. Anything that is very polar will typically stay at the bottom of the plate. Anything that is typically less polar, depending on how much less polar it is going to move up the plate with the solvent, the mobile phase, which is typically some sort of mixture of non-polar solvents. Now, this plate itself, that is called the stationary phase, and the reason it's called stationary is the media of the plate, that silica gel, that's not going to move. The solvent is what's moving across the plate, right? Right here we see a picture. This would be your TLC plate. You notice you're dotting it one end. You dot it above the level of the solvent. Be careful you don't submerge this dot. If you do, the solvent will just diffuse throughout this. The solute will just diffuse throughout the solvent here, and it will literally just be everywhere. You won't get any pattern here. You need it above so that your mobile phase will move through it and up. Okay, so your mobile phase after a while is going to be moving through, that's the solvent down here, is going to be moving up along your stationary phase, which is your plate. It is going to pick up the nonpolar components of this dot. Now, if you have extremely polar components, they won't move at all. If you have more polar components, so they're more polar, less nonpolar, they're going to move a little. And the less polar stuff is going to move the most. And if it's extremely nonpolar, it will actually move almost along the front, which is called your leading edge of your solvent right here. And it'll just move with this. In a real plate, they do not move in perfect circles like this. You will see them sort of spread out along the plate as they go across. They'll diffuse across. So you gotta be careful that you have not put dots right next to each other. All right. Notice that you do not want to leave this forever. You need to stop this after it gets up here somewhere. If you let it keep going, what you're going to find is these will just keep moving up to the top and they'll all bunch up here. You can't tell anything different anymore. So you and a friend are studying for a chemistry exam. What if your friend tells you, since exothermic processes are favored and the sign of enthalpy change tells us whether or not a process is endothermic or exothermic. The sign of delta H solution tells us whether or not a solution will form. How would you explain to your friend that this conclusion is not correct? What part, if any, of what your friend says is not correct? Okay, so again, exothermic processes, these are favored, yes. Okay. The sign of the enthalpy does determine whether it's endothermic or exothermic. So many of the components of this conclusion sound reasonable, right? The problem with this conclusion overall is it doesn't take into account any of those limiting factors that we talked about, does it? So what happens if you have very, very large delta H1 and 2? Then you may not be hot enough to actually form a solution, right? Or let's say that you continuously keep providing energy. Well, that actually will form a solution even if you have an endothermic delta H solution, because as long as you just keep providing energy, your solution will be formed. So you can actually have a very small delta H solution that is positive, that is not exothermic, is endothermic. And because room temperature provides you with energy, at room temperature, that will actually be a solution that will form. Okay? So you got to keep those things in mind. Yes, this does tell you how likely it is formed, but there's already energy in the environment at room temperature, and there is other factors that can cause the solution not to form. So decide whether liquid hexane, C6H14, or liquid methanol, CH3OH, is the more appropriate solvent for substances grease, which again is C20H42, and potassium iodide, Ki. And so what you're looking at here is polar versus nonpolar, right? Here you have something nonpolar, here you have something polar. This again is nonpolar, and this right here, this is ionic. And so this, for example, potassium iodide, it's not going to mix with hexane well, right? And that's because hexane is nonpolar and potassium iodide is ionic, which mixes with polar substances. So you can think of it as being polar. In the case of hexane and grease, these are going to mix well together. By the way, in these sort of questions where I ask you stuff and you may have actually tried that exact thing out, you may want to actually think about your life and whether this has worked in your life. So literally I'm talking about gasoline and grease that you get off the car. And so when you're working on an engine or working on something and you get grease on your hands, yes, you can use gasoline to cause it to dissolve off. You can use gasoline to clean it off your clothes and even your hands. Though your hands, it will cause damage to the hands to a degree. Not a lot, but a little. So repeated use will give you rough hands, if you're curious. Methanol here. Well, methanol is something solvents and alcohol. In fact, if you've ever used potassium iodide solution or iodide solution, you will have noticed that it smells like alcohol or it smells like ethanol. And usually these are made using ethanol, by the way. And so yes, you can use methanol to dilute or make a solution from potassium iodide. But again, this is polar versus nonpolar. So the nonpolar substances will dissolve one into the other, and the polar substances will dissolve one into the other. So yes, methanol dissolves Ki, hexane dissolves grease. The others don't work. Alright, so each of the following pairs, let's predict which substance would be more soluble in water. So the first one we have is NH3 and PH3. So which do you think will be more soluble in water? Well, which one has more like hydrogen bonds? Which one's less like hydrogen bonds of water? Well, the NH3 is more like hydrogen bonding, right? That actually makes hydrogen bonds. The PH3, those only make dipoles. So you can only have dipole-dipole interaction there. You can't have hydrogen bonding. And so NH3 is your answer. The other one right here, this right here is actually a acid right here. This is highly polar. This is going to be able to make hydrogen bonding because it has the OH right there. This right here does not have an OH. It only has a spot where it could receive hydrogen bonding. And so this one will be more soluble in water because it can more readily receive and make hydrogen bonding. It's more similar, better hydrogen bonding to the water molecules. This cannot make hydrogen bonds to the water molecules. It can only receive. So which of the following chemical or physical changes is an endothermic process? So what we're looking for is something that will suck up energy. First off, again, many of these questions you don't actually need to know anything about chemistry. You really just need to think a little, right? So endothermic, as long as you knew the endothermic, that means that sucks up energy. Combustion of gasoline is obviously not endothermic, right? That obviously releases a lot of energy. Evaporation of water. Well, have you ever sweat? You sweat when it's hot out, right? And so what that sweating is doing is you're releasing liquid water. That liquid water evaporates, causing you to cool down. Or if you've ever dunked yourself in water and then ran around on a hot day, you start getting cooled down, right? Because the water's evaporating off you. Freezing of water, well, that's going to be going from liquid water to solid water. And so that freezing of water is actually going to release energy. That's why you need a freezer to do it. The freezer is going to remove that released energy, thus freezing the water. The mixing of sulfuric acid in water. Actually, it's a great thing to actually feel this if you ever get a chance. It's kind of neat, tactile thing you get to experience because this is an example that you see a lot actually. Any strong, highly concentrated acid, when you mix it with water, is going to give off a lot of heat. And it actually gets very hot very quickly. I've actually had plastic objects that I've been using sort of get soft on me. They haven't quite melted, but yeah, they've gotten soft and moldable. Every now and then I get a cheap piece of plastic, I guess. That is what it is. Now, so we've seen the evaporation of water would be our endothermic process. And that's something we actually comes out of the last chapter if you were to think about it a little bit. Structure effects. So vitamins can be used to study a relationship among molecular structure, polarity, and solubility. One of the reasons this is so important, in fact, is for vitamin retention, this relationship, especially among the fact of the mobile phase versus non-mobile phase, or polarity, non-polar versus polar, is actually extremely important. All right, so you may have heard of fat-soluble vitamins before, and those are vitamins A, D, E, and K. They are all fat-soluble vitamins. The reason they're referred to as fat-soluble vitamins is they are soluble in fats, meaning they are non-polar. Fats are non-polar, and these vitamins are non-polar. That's why they're soluble in each other. These are considered hydrophobic, which means water-fearing. That means they don't dissolve well in water, which is what your blood is mostly composed of. And so these can actually build up in fatty tissues of the body. What that means is that if you ate vitamin A, D, E, or K in sufficient quantities sometime in the last year or two, you're probably good. Okay? You don't need to eat these every few days. You're good if you just eat them once every now and then. Okay? I wouldn't recommend waiting, years between. That would be kind of ridiculous. But you probably only need to eat them like once a month. All right? As long as you get enough overall, you're good. On the other hand, we have water-soluble vitamins. Water-soluble vitamins are going to be vitamins B and C. And these are actually polar. What that means is these are considered hydrophilic, which means water-loving. That means they dissolve in your blood, they dissolve in your water. You're going to urinate vitamins B and C out every day. And that means that you have to actually consume vitamins B and C regularly. You can get away with not eating them for a day or two, but if you don't eat some vitamin C every few days, you'll actually start developing scurvy and a number of other different unpleasant side effects. So vitamin B also is another concern, but that will just slowly make you less healthy over time. Vitamin C actually is something that college students regularly do not eat enough, and so you regularly get cases of scurvy, what used to kill pirates back in the 1700s, uh, popping up on college campuses because the students don't take any vitamins and don't eat any, just eat pizza all the time, don't eat any fruits, fresh fruits usually. Uh, anyways, if you don't consume these regularly, they don't build up in fat, they get urinated out, and you end up needing them regularly to be replenished. You can't build them up long term. So let's talk about some pressure effects. So we've been talking about how to make solutions, what affects solutions. In a solution that has a gas dissolving in a liquid usually, pressure effects are going to increase your solubility of your gas. So Henry's law, the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. Henry's law can be mathematically stated as the concentration of your dissolved gas equals a constant times the partial pressure of your gaseous solute that is above the solution. Notice that K is actually what sets your units here, if you're curious. Now, Henry's law is just what happens. That's what law is. So this just tells you what happens. It's reaffirmed every day, over and over and over, by every body of water and cup of water and soda in the world. Okay? However, the theory behind it goes as so. So this schematic is sort of showing you at a molecular level what's happening. So when you have a partial pressure of your gas molecules above a solution, what you're seeing is every now and then you will have molecules that are in the solution that are going to escape to above the solution. But at the same rate, you're going to have molecules that are in the air above the solution, hit the solution, and they will come back down. Now, if the pressure is low, then there's less likelihood that these molecules will hit the solution and thus come back into solution. If you have a higher pressure, that's going to increase the likelihood that these molecules are going to slam into the solution and become get up to again, that they will form the solution. If you have less pressure, then you'll have less chance of these molecules hitting the solution and coming back in, and thus your net outflow is going to be greater. The greater the pressure, the more the net inflow will be greater. Now let's actually use this as a concrete example, okay? So everybody's probably opened a carbonated drink. This could be beer, this could be champagne, this could be soda, this could be fizzy water, whatever. I don't care. Carbonated drink, okay? Now, when you first open the carbonated drink, it goes psh, and that psh sound is because it is releasing pressure. It was under pressure. When you open it, it releases that pressure. And the reason for it being under pressure is when they make a carbonated drink, they take CO2 gas, they put it under pressure so it absorbs into the soda or whatever you're talking about, the solution. And that's how they get it carbonated. It's literally absorbed more CO2 into the solution than it would normally be in water. And so, when you open the cap, you've reduced the partial pressure above it, and so CO2 is going to start flowing out of the solution. And what does that mean? Well, for the next hour or two, that carbonated drink is going to taste like it should, right? It's going to have lots of CO2 in it. But after a few hours, you're going to start seeing it'll get more and more flat, right? You'll have less bubbly. And that's because your CO2 is escaping the solution out into the atmosphere because the partial pressure above it is lower. You've lowered that partial pressure. So one of the ways you can keep that from happening is you can, of course, cap the bottle. If you cap the bottle, that keeps the CO2 that escapes still in the bottle. So some of that will actually get recycled back into the solution when it hits it. And that will slow the release of the CO2 from the solution. If you want to slow it down even more, you can actually apply a little bit of pressure to the top so there's less volume up there. And that will actually keep the carbonation in there longer. Of course, the real factor of these is the fact that it's going to leak from that cap now that's open. The cap just isn't sealed as tightly. So the tighter you get the seal, the less volume above it, the longer it will stay carbonated. But it's going to be impossible for you to do a perfect job of this, so just know that it'll eventually go flat. In fact, even soft drinks that are properly bottled by the company go flat after a time, right? If anybody's bought something after its expiration date by accident or forgotten it in your car or something, and then you try it out, a year or two later, you'll realize it's flat, yuck, and throw it away. And that is, of course, because even their capping process can't keep the CO2 in there forever. All right, so right here's an interactive example using Henry's law. A certain soft drink is bottled so that a bottle at 25 degrees Celsius contains CO2 gas at a pressure of 5 atmospheres over the liquid. Assuming that the partial pressure of CO2 in the atmosphere is 4 times 10 to the negative fourth, notice that is a very, very big difference, atmospheres, calculate the equilibrium concentrations of CO2 in the soda both before and after the bottle is opened. Okay, so the Henry's law constant for CO2 in aqueous solution is 3.1 times 10 to the negative 2 moles per liter times atmosphere. And that's that constant value that I mentioned that sets all of your units. This is at 25 degrees Celsius. Depending on the temperature, you will actually get different values for this, by the way. So it is temperature dependent. They gave you this for the temperature you're looking at right here. So that's good. So the next thing we're going to do is, what's the Henry's law for CO2? Well, we take Henry's law, the concentration equals that constant times the partial pressure. The next thing we need to do is K, we put that value in. And so now we can move on to the rest of the problem. So what is the CO2 in the unopened bottle? Well, the partial pressure is 5 atmospheres. That's what was given to us. So all we have to do is just plug that 5 atmospheres, multiply it by that K value, and that's going to give us our concentrations in moles per liter, which again, moles per liter is right here, moles per liter being molarity. And so that's the concentration and molarity of CO2 in the unopened bottle, which is 0.16 molarity. All right, so what about the open bottle that you've let equilibrize, that's been sitting there for a while? So in the open bottle, the CO2 in the soda eventually is going to reach your equilibrium with your atmospheric CO2. And that's going to be what happens every time you have something open to the atmosphere or open to another container, is they will always reach equilibrium. So in this case, the atmosphere essentially has an unlimited amount of space and CO2 as compared to your bottle, right? And so you're going to be equal to the atmosphere eventually, and that will be your equilibrium. So what we use is the pressure of the CO2, the partial pressure of CO2 in the atmosphere. That's going to be what our bottle will be after it's open for a few hours. So the large change in concentration of CO2 is actually your soda getting flat. That's because you'll notice that the concentration of your CO2 in the soda is vastly less. So we have K here. We multiply it by the partial pressure in the atmosphere, which is going to be what's in your bottle once you've left it open long enough. And that will then give us our number, that is our concentration and molarity. This 1.2 times 10 to the negative 5 versus 0.16, that is thousands of times different. That is a huge difference in your concentration of CO2, of course. All right, so what happens with temperatures for aqueous solutions? What factors does temperature have on aqueous solutions? So if you have a solid, then the solid will always dissolve more rapidly at higher temperatures. You have more energy to break apart those solute-solute and solvent-solvent interactions. It's going to happen a lot faster. The amount of solid that can be dissolved may increase or decrease with increasing temperature. There isn't a completely solid trend, if you will excuse me for using the term. The solubilities of some substances will decrease with increasing temperature, but typically what the pattern is the majority of solutions will actually have an increase in solubility with increasing temperatures for solids dissolving in liquids. Okay? Overall, mostly. But there is not a completely set pattern there. You cannot just say for a fact it is this. Predicting the temperature dependence of solubility is actually quite difficult to do. It is not something that's easy to do. So right here, this is gases and liquids. And what you will see is the solubility of a gas in a liquid will actually go down as you increase the temperature. Gases will become less soluble in liquids as you increase temperature. The lower the temperature is, the more soluble gases will be in liquids. And this one actually is a very standardized, very predictable pattern. Though it depends on the species, the gas, how much the solubility changes per temperature. As you can see, helium doesn't have a lot of difference. Methane has a huge amount of difference. Now, one of the things you can think of here is gases, when they go out to the atmosphere, that's actually a higher energy state when it's in the gaseous form. And so as you increase the energy, i.e. increase the temperature, that's typically going to mean the gas will be going into the gaseous phase easier. As you decrease the temperature, you will typically cause it to go into the liquid phase or the solution phase easier. One of the interesting things that many of you probably knew to some degree, but may not have realized, is that this actually has a huge effect on the world as we know it. And so, one of the things you may have realized and noticed is that at the equator, the water is very pure and doesn't have a lot of fish. They don't have these huge schools of fish everywhere like they do at the North Pole. Okay? The reason for that being that they don't have the density of fish, most of the fishing activities don't happen at the equator, is because the temperature at the equator is higher. That means there's less oxygen dissolved in the water. The temperature at the poles is lower, meaning there's more oxygen dissolved in the water, and thus the fish can breathe easier. And so you actually do see a slight pattern where you get more animals typically at the poles, less animals in the water, typically at the equator. On the ground it's different, but in the water, that's why. So the solubility of gas in water decreases with increased temperature. Water used for industrial cooling is going to be returned to the natural source at a higher than ambient temperatures because it will have been warmed due to the fact that it was used for various different industrial processes. This is actually referred to as thermal pollution, and what happens is that warm water tends to float over the cooler water. This will block oxygen absorption. This leads to the formation of a Boiler scale. And one of the big things is this is going to make it harder for the fish under to breathe. Therefore, it's going to start killing off a lot of animals under the water, even though the only thing you're doing is your water is just a little warmer than what you're putting it in. They don't have any other pollution that's going on, just warmth, thermal pollution. And so this can cause some kind of interesting properties. First off, the anaerobic microorganisms that typically float in water will actually find the warmer water to be easier to breathe in, and so it can cause things like algae blooms, uh, especially considering the fact that it may be killing off some of the animals that are already there due to lower oxygen levels, thus giving them more food to eat as well. So it does cause some issues if this is done on large scales. Small scales, not as much, but larger scales, it can cause some serious issues. Let's rank the following compounds according to increasing solubility in water. And so what you're looking for is more polar, less nonpolar behavior. So for example, right here we have an OH, that would be polar. Right here we have the CH3 part, that would be nonpolar portion of this compound. And so this has a lot of polar characteristic, not a lot of nonpolar characteristic. This one has a pretty good amount of polar, same as this, but has more nonpolar. This one right here has an oxygen, so it has some polar behavior. But it has a lot of CH3, CH2, so that's a lot of nonpolar behavior. This can't even make its own hydrogen bonding, it has to only accept hydrogen bonding. This can't make any hydrogen bonding at all. This is a nonpolar substance. And so, ironically, this is actually listed in the order of the numbers. So this is the least soluble in water, 1, 2 is more, 3 is more, and 4 is finally our most soluble in water, which is literally just down this list. Which statement below accurately describes the effect of increasing temperature on solubility? So, does solubility always increase? Solubility always decreases? Dissolving of a solid occurs more rapidly? Dissolving of a solid occurs more slowly? Or none of the above? Well, we know this isn't true, right? Because some of the solids, it actually decreases. The gases, if we increase temperature, it actually decreases solubility. We know this isn't always true. See the always? Because again, some of the solids will actually increase in solubility with increasing temperatures. So dissolving of a solid occurs more rapidly. Yeah, that's true. Because the more energy you have, the more easier, faster you can break those interactions to form the new interactions in your solvent. And so yes, that's true. An aqueous solution and pure water in an enclosed environment is what we're seeing right here. And what we can see is the solution with solute in it will actually have a draw, net draw, to the solvent, the pure solvent right here. And this is because this right here is going to seek to dilute this solute as much as possible. And so you will actually see that after a while, in this closed environment, you will actually get the majority of the water vapor collecting in here to make your aqueous solution. If this is big enough container here, you will actually see none of your water left in here. It will have all evaporated. So, the vapor pressures of your solutions. The presence of a non-volatile solute will always lower the vapor pressure of a solvent. This inhibits the escape of your solvent molecules from the liquid. So if you have solute molecules in a solvent, and the more solute molecules you have in a solvent, the higher the concentration, the less volatility of the solvent. Okay, so the less gas you will get above the solvent, the less the vapor pressure will be. This is actually given to you by Raoult's law. And Raoult's law is, again, it's a law, it's what's observed. It doesn't actually tell you why it happens. This will be the pressure of the solution. So that's the observed vapor pressure of the solution above it is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So what we'll see is if we have more solute, higher mole fraction, the pressure above it will be less than it would have been for the pure solvent. Non-volatile solute simply dilutes the solvent. So if we have a non-volatile solvent, something that won't go into vapor pressure, into the vapor phase itself, like salt is a great example, NaCl, then the solute is simply going to dilute your solvent and help to hold more of it in the solution, instead of the vapor. Alright, so if you look at Raoult's law here, you can notice that this is very similar to the linear equation you guys are probably used to. Here we have a y equals a slope times an x, and then we plus 0, so we don't have anything for b. Which makes sense. You would expect a pure solvent, if it is pure, i.e. it has no solute in it, to act as a pure solvent. So if there's no solute in it, it acts as a pure solvent. There you go. This can be represented, of course, by your linear equation. So the P is going to equal X is actually the chi, sorry. M is actually the pure solvent's partial pressure, which is a constant value because it is for the pure solvent. There you go. So the slope of the graph is going to be a straight line with a slope that will be equal to your pure solvent's vapor pressure. And right there, that would be a generalized plot of Raoult's law. And so you have your partial pressure of the solution. And right here you have chi. Keep in mind, chi is always going to be a value between 0 and 1. You can't go above 1. You can't have less than 0. You can't have less than 0 solute. And you can't have more than all of the molecules being solute. So, Raoult's law, by the way, won't actually go all the way to this one. It'll approach, but won't actually hit. All right, now let's try this out a little bit. So let's calculate the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of common table sugar. And it gives you the name and the molar mass. So sucrose is the most common table sugar. And its molar mass is 342.3 grams per mole. It then gives you a volume of water, so 643.5 cc or centimeters cubed of water. Remember, cc, centimeters cubed, is the same thing as milliliters. So at 25 degrees Celsius, the density of water is this, and that's grams per centimeter cubed, or cc, or milliliter, whatever you want to use. And the vapor pressure is 23.76 for that water, which would be pure water. And so the first thing we have to do is, again, we need to always, the good problem solving 101 always dictates you look at what you have, what you need, and where you want to get to. And so what do we want to get to? Well, we want the expected vapor pressure, right? The vapor pressure of the solution. 25 degrees, well, 25 degrees, we don't really need that number. It's just for verification. Here we're at 25 degrees. We have numbers for 25 degrees. That's great. Right here we have 158.0 grams, and we have a molar mass. That's going to be able to give us moles, isn't it? So we need to get chi. Here we have our moles. We're going to also have to use the water to figure out moles as well, so we can get chi, right? And so, well, we have a volume of water. Here we have a density. Density can get us into mass. Water is H2O, and so we also can get molar mass for water, which can give us moles, right? And then finally, right here, when we look at this, we have our vapor pressure for the pure solvent water. And so let's go ahead and get Raoult's law. Right there, our pressure of the solution equals chi times the pressure of the pure solvent. So let's start calculating these out. So we need chi, that means we need moles. So the first thing we're going to do is we're going to get moles of sucrose, because we have every number we need for that. So 158 grams of sucrose. This is going to be divided by the molar mass of the sucrose. So 1 mole over 342.3 grams, which will give us our moles of sucrose left. Notice grams cancel. And that is 0.4616 moles of sucrose. The next part we need to do is we need to figure out the moles of water. And so we have a volume, we have a density. Volume doesn't really have a nice relationship to moles, does it? But we know that mass has a very nice relationship to moles. And so we're going to go ahead and get that into mass first. Now this is 643.5 milliliters or cc's of water. This is then going to be multiplied by our density, which is 0.9971 grams over 1 cc. Again, that's the numbers that were given to us. That gives us our mass of water, which is 641.6 grams. Alright, so the number of moles of water then is going to be our mass divided by our molar mass. Where do we get our molar mass? Well, we look at the formula, H2O, water. We look at our periodic table, we add those hydrogens and oxygens together, and that gives us our molar mass. So that's, I'm going to stop saying that, by the way, by now. By now you really should have that down. If you do not, you very, very badly need to go back and practice chapters 1. And ironically, you should have had that practice through almost every chapter in the entirety of General Chemistry 1, and you actually still need it even up to today. It's just never going to go away. So anyways, please make sure you have that down, because I'm going to assume from now on that you know what the hell that is. That doesn't need a restatement. So here you take your mass divided by molar mass. You then get your moles from that, 35.60 moles. What is your mole fraction? Well, again, it's going to be moles of what you're talking about divided by the moles of the complete solution. And so we're talking about water here. That was chi of water. Otherwise, you can go, well, I want the partial pressure water, right? So I need water. So what you'll see here is you have your moles of water divided by your total moles down here. And so it's going to be 35.6 moles of water divided by your 35.6 moles of water again, plus your 0.4616 moles of that sucrose sugar. By the way, if you ever forget what needs to be on top for whatever reason, if you just look at Raoult's law, it tells you that. Okay, so if you had this chi was 1 because it was all water, and this pressure right here would be equal to this, wouldn't it? And that means it's pure water. If you had 0 here, you don't have any water, then the partial pressure is not going to be equal. It's going to be 0. You're going to not have any water to go in the vapor phase, which means the partial pressure is 0, right? Okay. By the way, if you're wondering why I keep doing that, going back and trying to give you the logical framework, figuring out what means what, why we have those things, there's 2 reasons. Number 1, I'm trying to build up your critical thinking skills. The second part of that is good science. Good science says that all of the people I train, all of you future scientists, all of you future biologists, chemists, you would know how to go back and double check these basic laws, tenets, and theories that you've been taught. And you should. And then you should try to prove them wrong. That's good science. Good science is not just believing what I tell you. Good science is trying to prove them wrong. And when you fail to prove them wrong, which hopefully you will prove them wrong, because that would make a big breakthrough, but if you fail to prove them wrong, then you just go, okay, whatever, I'll keep using it. Okay? But ideally, you would actually try to prove these things wrong. So what is the mole fraction of water in the solution? So I again have my value of chi, which is 0.9873. Notice it's a very close to 1 because you actually have very little mass of the sugar. Or moles of the sugar, excuse me. You actually have a fairly large mass. So the vapor pressure of your solution is going to be, again, you take Rayleigh's law, you substitute the values you have, which are these two over here. So you have chi times this partial pressure. This, by the way, partial pressure not. That means the standard partial pressures, if you ever see not. And so you just multiply these values. You're going to get an answer that's in torr. You will notice that you do not have any units for chi. It's a unitless number because the moles actually cancels out. And that means you have a vapor pressure for the solution of 23.76 torr in the pure state to 23.46 torr in the solution. And so that vapor pressure has lowered by a 0.3 torr. All right, now, lowering of the vapor pressure. This is going to help in counting molecules. This can provide a means to experimentally determine your molar masses. And usually you would do a lab that would involve figuring out the molar mass of a substance based on Rayleigh's law and the lowering of its vapor pressure. I actually don't know right now. If you are doing that, you guys will have to tell me sometime, I guess. Anyways, this is actually originally how they figured out molar masses for substances. This is the original experiments that were done to do it. They actually gave very good values, very close to the actual values. There are newer methods you can use to get slightly more accurate values for most compounds. Rayleigh's law helps ascertain the number of moles of a solute present in a solution. It's actually a fairly quick and easy way you can do this very reliably versus less reliable methods that many people try to do spectroscopically or automated. So you think that this might be old, but it's not. It's something that, yeah, it was done 200 years ago, well, almost 200 years ago, but you still have it being done today in labs to verify results. You still get this done. This can help characterize solutions. This provides valuable information about the nature of the solute after it dissolves. So before Rayleigh's law sort of tells us an ideal solution, if you will, now we need to talk about non-ideal solutions. So in non-ideal solutions, both components are going to be volatile and liquid-liquid solutions. So this will contribute to the total vapor pressure. In the case that you have this where both are volatile, you need to use a modified Rayleigh's law. Essentially, you have to do Rayleigh's law for both of them. So what you get is you get 1A for species A that is volatile. And this is going to tell you that the pressure above for that solution for species A is going to equal the chi of A times its pure solution vapor pressure. For solution B, for liquid B, that's also volatile, the pressure of that gaseous phase B over the solution is going to be equal to chi B times its pure solution vapor pressure. And so the total pressure over the solution is going to just be those two pressures added together. And so that total pressure will be the vapor pressure of the solution containing A and B over this liquid portion of the solution. Chi A and chi B are again going to be the mole fractions of A with respect to A for A. Chi B would be the mole fraction with respect to B. And again, these are just, you can get it. I think you understand. So an ideal solution, this would be a liquid-liquid solution that obeys Rayleigh's law. Nearly ideal behavior is observed when the solute, solvent, and solute-solvent interactions are all similar. The further you get from them all being similar, the less ideal the solution becomes. So if you have things that are very similar in their actions, such as nonpolar with nonpolar, polar with other polar, you are going to typically see a very close to ideal solution that will obey Raoult's law. So when delta H solution is large and negative, this means that strong interactions exist between the solvent and the solute. This is going to give you a negative deviation from Raoult's law. At least you will expect a negative deviation from Raoult's law. So both the components will have a low tendency to escape in the solution than in pure liquids. What that means is that when you have very large interactions, you're going to have a harder time getting them to escape to the gas. And so you will have a negative relationship to Raoult's law. You will have a negative deviation. This is a great example, acetone versus water. Acetone actually is very easy, is very volatile. If you take acetone and just leave it out, you'll have large containers of it evaporate in a few hours. Water also evaporates, but not anywhere near as fast as acetone. If you mix acetone and water into a solution, you will actually find that the acetone does not evaporate very fast. It in fact evaporates very slowly, similar to how the water evaporates. And so you get a large negative deviation from Raoult's law with this acetone water solution. When the delta solution is positive, endothermic, solute-solvent interactions will be weaker than what you would expect. And so molecules in the solution will have a higher tendency to escape. There will be a positive deviation from Raoult's law. And a great example of this is things like ethanol and hexane. So hexanes normally actually don't evaporate that fast. That would be things like gasoline. Ethanol also doesn't evaporate as fast, which is things like if you get very, very pure moonshine, or if you get the 95% ethanol that you'd use to in the lab. Now, when you mix these two things together, what you'll see is that the one that's in least, it typically evaporates much faster. And that's because you have a positive deviation from Raoult's law, because they don't interact with each other well. In fact, you have broken the interactions by putting the solute in. So putting this ethanol in a bunch of hexane molecules, you're actually breaking those interactions and causing them to interact worse, had to have weaker interactions. And so it tends to evaporate faster. So if you have a solution where they are very, very similar liquids, so the delta solution is very close to zero, the solution will closely obey Raoult's law. It's very, very close to an ideal solution then. And it will be very close to what Raoult's law is. So for example, when you have benzene and toluene, these are very similar, and so you have very little difference between them. You can pretty much freely replace benzene with toluene here, and this means that it will obey Raoult's law very well, because there's not a lot of difference in the interaction between two benzenes and a benzene and toluene. There just isn't much difference. So a solution is prepared by mixing 5.81 grams of acetone, which is right here, there's its molar mass, and 11.9 grams of chloroform, which is right here, and this is the molar mass. At 35 degrees Celsius, the solution has a total vapor pressure of 260 torr. So first off, would this be an ideal solution? And the vapor pressures of pure acetone and pure chloroform are 345 and 293 torr, respectively. So, first off, this actually tells you right away that this solution has a total vapor pressure of 260 torr. Well, it's not even between these, is it? It's actually a lower vapor pressure than these two would respectively be. So first off, is it an ideal solution? Well, you have something right here. Let's just go through. Okay, so the first thing you have to think about is this an ideal solution? And so you have an acetone and chloroform. You can label these A and C if you would like to help you when you do your calculations. So the calculated value can then be compared with our observed vapor pressure. So the first thing we would do is we have an observed, which we are given right here, right? That's 260 torr. So we should go ahead and try using Raoult's law and see if we get 263, or do we get something different? If it closely matches the observed value, then yeah, it's an ideal solution. Great. If it's very far apart, then we actually know then both that's non-ideal and how it deviates. So let's go ahead and calculate the number of moles of acetone and chloroform. Right here we have grams of acetone, we use the molar mass, and we get moles. Right here we again have grams, we use the molar mass, we get moles. By the way, you'll notice most of my problems I give you on these slides are usually 1 or 0.1 so that the math is easy. The solution is going to contain equal numbers of moles of acetone and chloroform. And so we see that our chi's will actually be 0.5 in both cases, half, because half of it's acetone, half of it's chloroform, right? So our expected vapor pressure is going to be 0.5 times the pure solution plus 0.5 times the pure solution. You would expect it to be halfway in between these two. By the way, when you have two solutions, you would typically expect the resulting, if it's an ideal, to be somewhere between these. Because literally you have a 0 to 1 here, this number, 0 to 1 here, this number. You're doing some sort of form of averaging, if you will. It's not quite an averaging because you can not be 0.5 here. But it typically is going to be something between these two numbers if it's ideal. And so if in the ideal case here, we get 319 torr because it's literally an average here. We take that 319 torr, we then compare it to the 260 torr that we saw from the experimental data, and we see that this is not anywhere near ideal. In fact, this is actually very far from it. In this case, it is not ideal in any stretch of the imagination. So this observed value is lower than expected, quite lower actually. This is a negative deviation, meaning lower, negative, going down. From Raoult's law, this can be explained in terms of the hydrogen bonding interactions, which is going to lower the tendency of these two molecules to escape from solution. So what we see here is that chloroform and acetone, these are both polar. Okay, and so our chloroform here has an H connected to this carbon that has a bunch of chlorines off of it, meaning it'll have a positive charge here, negative charge here. Our acetone is going to have a negative charge on the oxygen and a positive charge here over on the carbon. And so this is going to make something very similar to a hydrogen bond. It's not actually a hydrogen bond per se, but it's very, very close to it. And so the interactions between acetone and chloroform are actually stronger than you'd have the interactions between acetone and acetone or in chloroform and chloroform. Because you'll notice chloroform doesn't have a very strong negatively charged atom for this hydrogen to interact with versus the oxygen here. You'll notice the acetone does not have an H to do hydrogen bonding with. And so this, again, doesn't get this hydrogen bonding-like behavior. And so, yes, it makes sense that these interactions are actually stronger together. And so you have less vapor pressure. It's harder to escape into the gaseous phase. Excellent. Which of the following statements are true? By the way, one of the reasons I always go back, I know I do this, I forget sometimes to do stuff when I have you guys around me to see your reactions. One of the reasons I always sort of go back and recap, does this answer make sense? You should always do that for any science problem. And really, any problem solving you do, did the answer I just give make sense? Or does this violate everything I know? And then you should double check if it does. For example, if you were to do the mass of a feather, you did the math for it, and suddenly you got the mass of a car, you should go back and double check that, right? Which of the following statements are true? A liquid-liquid solution is called an ideal solution if. So 1, it obeys PV equals nRT. That's the ideal gas law, isn't it? This is the ideal solution, not ideal gas law. 2, it obeys Raoult's law. Well, Raoult's law is actually the one we're talking about here, right? Ideal solution. Cool, Raoult's law. 3, it's solute, solvent, and solute-solvent interactions are very similar. Okay, so that's actually the basis that we talked about for ideal solutions, isn't it? That all the interactions are very similar. There's not a lot of differences. 4, its solute, solvent, and solute-solvent interactions are quite different. Well, if they're very different, then if you mix them together, it's either going to be much easier or much harder for the solvent-solute interactions to be broken, and thus you'll have a very different vapor pressure, a very different evaporation. All right, so which one is it? Well, it is the 2 and 3, the ones in the middle. That is the answer. A solution is made by mixing hexane, which is this formula here, and chloroform, which is this right here. What type of deviation from Raoult's law is expected for this solution? And so we're again looking at something right here. Hopefully when you look at this, you go, or at least hexane, and the half dozen times I seem to have probably used this, you go, hey, that's nonpolar. And this chloroform right here, hopefully when you look at this and you see a hydrogen with a bunch of chlorines, you go, oh, that's probably polar. Or the fact that we've used that, like 3 or 4 times. Anyways, so you have a nonpolar and polar substance. That means their interactions are going to be quite different. So what type of deviation do you expect from Raoult's law for the solution? Well, you definitely expect a deviation, right? And in this case, they're going to be a positive deviation because when you add these chloroforms, well, let's look either way, okay? So I'm going to say that we have the solvent as hexane and the solute as chloroform. So the hexanes are going to interact with London dispersion forces. As we add chloroforms, those won't interact as well using London dispersion forces. They'll actually weaken the interactions of the hexane. That means it will go into the vapor phase easier. That means it will have more vapor, that being a positive deviation. Up, positive, higher. All right, let's look the other way. So if we had a solvent that was chloroform, we added hexanes to it. Now, the chloroforms are going to do dipole-dipole interactions. Those are quite strong. These right here cannot do dipole-dipole interactions. They can only do the London dispersion forces, which are much weaker. And so as you add hexanes, they're going to get in the way and not allow these dipole-dipole interactions that you should have had to form as easily. And so that will make it easier to go into solution, or easier to go into the vapor phase, and thus this will be a positive deviation. A solution is made by mixing ethyl alcohol and water. What type of deviation from Raoult's law is expected for this solution? Well, hopefully when you look at these, you go, okay, these can make hydrogen bonding, but this isn't going to be quite as good at making hydrogen bonding as the water, will it? And so what you're going to see is this actually gives us a negative deviation from Raoult's law. By the way, if any of you have ever put Jägermeister or any high alcohol content in the freezer, you will have actually taken part in this demonstration. So the reason that those don't freeze when they're in the freezer is because they have a negative deviation from Raoult's law from the pure solvent, the pure solution. Anyways, we'll talk more about freezing point depression as well. That is going to be the ultimate showing you that. Okay, so here, the interaction of the water and the ethanol, these ethanol interactions are actually going to be stronger than they normally would be. And so yes, you will get a negative deviation using that. So let's try hexane and octane. These both do London dispersion forces only. And so they are both nonpolar. You wouldn't expect a large difference between them. Their masses are about the same. If you had one whose mass was much larger than the other, then maybe. But no, it's very similar. You have very similar interactions. You wouldn't expect any deviation from this. So a solution of two liquids, A and B, shows negative deviation from Rayleigh's law. What does this mean? So, A, molecules of A interact strongly with other A-type molecules. Okay, so in this you have A and B. You have a negative deviation from Rayleigh's law. So that means they don't go into the vapor pressure as easily, right? They don't go into vapor as easily. And what you'd think is then that A and B need to interact very strongly, right? So the molecules of A interact strongly with other A-type molecules. The two liquids have a positive heat of solution, or the molecules, here, go ahead and read them. I'm getting, my voice is getting tired. Too much lecturing. All right, so the answer here is E. And the reason for this is molecules of A are going to interact more strongly with B-type molecules than with A, and the B will interact more strongly with A than they would with other Bs. And you know this because we have a negative deviation. What that means is the A's have to go into the vapor phase easier, the B's have to go into the vapor phase easier when they're separate solutions. When they're mixed together, they need to go into the vapor phase less often, which means stronger interactions. A salt solution sits in an open beaker. Assuming constant temperature and pressure, what will happen to the vapor pressure of the solution? Okay, so we have a salt solution sitting in an open beaker. What's going to happen is that if we have constant temperature and pressure, the vapor pressure is first, it might lose some water, okay? If it loses water, that's going to be that vapor pressure over the solution, right? But when it loses water, what's going to happen to the volume? Well, the volume will shrink. And that means that solution is getting more and more concentrated the more vapor it puts off, the more water that escapes. And so it's going to actually cause the vapor pressure to decrease the more concentrated it gets, right? That chi is going to go down. And so we have this vapor pressure decreasing over time for a salt solution. So colligative properties, these are going to depend on the number of solute particles in ideal solution. These do not depend on the identity of the solute particles. So whether you have, as long as it's an ideal solution, keep that in mind, whether you have hexane versus octane versus pentane, it doesn't really matter, okay? You don't care. Or heptane, all different types of alkanes, none of that matters. What matters is only the number of solute particles. So these colligative properties, they're going to include things like boiling point elevation, freezing point depression, and osmotic pressure. By the way, I'm going to go through all three of those if you're wondering. This is going to help you determine the nature of a solute after it's dissolved in a solvent. Remember that you don't always get to mix things together when you have to work in labs or if you have to work on the real world. Usually you're given solutions when they've been sitting around for a while, either from somebody or something, right? And you collect it and then you have to figure out what the hell it is or how much of something is in it. So you need to be able to work on solutions. This is a great way of being able to work on solutions without having to disassemble them, which is not really possible, at least not without losing things. The molar masses of substances can also be determined using colligative properties. So boiling point elevation. Non-volatile solutes will elevate the boiling point of the solvent. This is actually partially what we saw in Rayleigh's law. It's just that looked at vapor pressure. This looks at boiling points. So the magnitude of the boiling point elevation will depend on the concentration of the solute. Your change in your boiling point can be represented as follows, which is going to be your boiling point elevation formula. So you have your boiling point elevation, how much your boiling point goes up. This is going to be equal to a molal boiling point elevation constant. It's just a constant that depends on what solvent you have. If you have water, if you have hexane, if you have whatever your solvent is, it'll have its value for K. That'll be times the molality. Notice I said molality will be useful later on. Here you go. Molality of your solute. So that will be your moles of your solute divided by kilograms of solvent. By the way, notice this constant here is a value for your solvent. And so these actually end up canceling out. Your kilograms of solvent cancels out a portion of this K. So again, that's your molality. So right here we can actually see a phase diagram if we look at pure water and for an aqueous solution containing a non-volatile solute. And so what we see here is we have a freezing point depression and we have a boiling point elevation. Here being pure water, here being your solution. All right. By the way, many of you may have actually taken advantage of this at some point in time where you do things like put a little salt in, water, so you can get the temperature of the water higher and thus boil the noodles at the temperature you want them to boil, or etc. Okay. The freezing point, well, I'll talk about the freezing points in a bit, but right here this shows some different compounds and their KBs and their boiling points and freezing points. By the way, this is KB for boiling, this is KF for freezing. You will notice when we get to the freezing that it looks exactly the same. You do almost everything the same. It's just one's an elevation, means goes up. The other's a depression, which means goes down. So, a solution was prepared by dissolving 18 grams. Okay, so you dissolved 18 grams of glucose in 150 grams of water. And the resulting solution was found to have a boiling point of 100.34 degrees Celsius. Notice this would be the boiling point plus the change in the boiling point. That is not the change, okay? One thing that people tend to mess up on and causes them a great deal of funny, interesting answers is they get a total boiling point or they get the elevation and they mistake one for the other, which usually there are a difference of at least 100 degrees between them. Alright, so let's calculate the molar mass of glucose. Glucose is a molecular solid that is present as individual molecules in solution. One of the things I have not mentioned yet for this is that colligative properties, if you have a compound, a solute, that splits apart and dissolves in parts when it dissolves in your solution, then that is going to count as multiple portions, multiple particles. You notice that I used that word particles rather than molecules, atoms, any of these other words I could have chosen. And the reason for that is, in this case, glucose only dissolves as a single individual molecule. So for every molecule of glucose you get dissolving, every mole of glucose you end up dissolving, you have the same number of particles. Okay? So one molecule of glucose dissolves as one particle. It's just one piece. It doesn't split. 1 mole of glucose would dissolve as 1 mole of particles. Now, if you had something that splits apart, let's say something like sodium chloride. Sodium chloride is actually going to split into 2 particles, the sodium and the chloride. And thus, if you had 1 mole of sodium chloride dissolving, that's actually 2 moles of particles dissolving. If you had something like MgCl2, that would be an Mg dissolving and 2 Cl's, right? Dissolving, which is a total of 3 particles. That means that 1 mole of MgCl2 dissolving is going to give you 3 moles of particles dissolving. All right, so in this case, we don't have to worry about all that. We just have glucose dissolves as an individual molecule, and that's why that's stated there, so you can more easily put your mind at ease. Okay, so we have here a freezing point, or I'm sorry, I'm doing boiling point elevation. So we have our value that is resulting from that elevation. We have the mass of water, we have mass of glucose. We need to calculate our molar mass. And that means we need to ultimately calculate out moles because we already have mass, don't we? And so we first need to get our change in temperature, that boiling point elevation. So what's the boiling point of water? Well, it's 100 degrees Celsius. And so we subtract off 100 degrees Celsius from this 100.34. And that gives us our elevation, which is 0.34 degrees. Notice that if you get a negative value out of that, that obviously is not an elevation. And so you should seriously look at your math and go, did I do something wrong? So for water, Kb equals 0.51. You can look it up, or typically I give it to you in problems, or at least they give you a table for the exam. The molality of the solution then can be calculated by rearranging the boiling point elevation equation. So we have these two values of that boiling point elevation equation. We just need to rearrange it so they're on one side. So here we have the equation. We're going to plug this in right here. This goes in right here. We'll be left with our molality. Ooh, voice is going out. The solution was again prepared using 0.1500 kilograms of water. I got this from the grams. Again, you just divide by 1,000. Hopefully you know these by now. If you don't, you really need to do some reviewing. Very, very, very badly. So using the definition of molality, we can find the number of moles of glucose in the solution. So we're first going to get that molality. And right here we get and solve the molality from that boiling point elevation equation we looked at before. So we plug our values in, we've rearranged it so the molality equaled the temperature elevation over K. We plug the values in, we do our math, we get 0.67 moles per kilogram. You will notice this kilogram here, because this is molality, this needs to be the kilograms of solvent. Our solvent is water. So once we have our kilograms of water, we can just multiply this number by that kilograms of water. And congratulations, we now have our moles of our solute. And so we get our moles of our solute, which is 0.1 moles of our solute. Therefore, we have 0.1 moles of glucose. It had a mass of 18 grams. So to get a molar mass, you always take grams mass divided by moles. And so we take our 18 grams divided by 0.1 moles, and that will give us 180 grams per mole, which is the molar mass of glucose. Okay, so the next one is going to be freezing point depression. When a solute is dissolved in a solvent, the freezing point of the solution is going to be lower than that of the pure solvent. You've all experienced this at some point. So when it gets icy out and it's icy conditions, what do? They spread salt on the roads, right? And so what they're trying to take advantage of is they're trying to take advantage of this freezing point depression. So water, whenever you have something frozen, that water, what actually makes the ice slick, ice is not slick in and of itself. What makes it slick is that the top layer will actually melt slightly. And that melted water is what makes it slick. So when that top layer slightly melts, which will randomly happen all the time, it will mix with the salt they pour on it. That's going to make a solution. And that solution is going to have its freezing point elevated, which means it's harder to freeze back in place. It would need to be colder to freeze that. Okay? And so that causes it to break up the ice and make it into slush because it's going to cause more and more of that water not to freeze the more salt you have on it, right? And hopefully it would cause it to melt and go off, and then you don't have any ice on there at all. But not always. So anyways, again, you're taking advantage of the freezing point depression, making it go into the solution rather than the solid instead. So water in a solution has lower vapor pressure than that of pure ice. And remember, you can envision everything going back and forth, going through the vapor phase to do so, if you would like. Because the vapor phase is the individual molecules, if you will, moving around and not in conjunction with each other, whereas the liquid and solid would be them in interactions with each other. And so when they break apart, they can then reform. And it's an easy way to think about these. As the solution is cooled, the vapor pressure of ice and that of liquid water will become equal. The temperature at this point is below 0 degrees Celsius, and the freezing point will have then been depressed. Right here we see an example of it at a molecular level. And so right here, this is ice that's in equilibrium with water. So the ice in equilibrium with liquid water to contain a dissolved solute is going to have to interact with the solute. When we try to join them back into the water, we will have to break these solute-solvent interactions here. And so that will depress this freezing point, make it harder to freeze. Right here is the freezing point depression equation. Notice it is the exact same, it just has a KF instead, and this will end up being a depression, which means down. So negative. It really is the exact same. Even the name of the KF, mole freezing point depression constant, is exactly the same sort of thing, just freezing point depression now. This is actually used to ascertain molar masses and characterize solutions, just like the boiling point elevations. Really the big difference here is it easier to boil something or is it easier to freeze it? That's usually your big difference here. So let's try this out. Let's calculate the freezing point and boiling point of an antifreeze solution that is 50% by mass ethylene glycol, which is this compound right here, in water. Ethylene glycol is a non-electrolyte. If you remember back in the previous chapter, or way back in General Chemistry 1, electrolytes split apart in solution, like salts and ACl. Non-electrolytes are things like ethylene glycol, glucose, that do not split apart in solution. And so this will dissolve as a single molecule just like so. In water, it will not split apart, meaning for every mole we also will have a single particle. Or a single mole of particles. Excuse me. This right here is the temperature of freezing. 229.9 degrees Celsius. This is the temperature of boiling. Okay, this is obviously my slides is messed up. The boiling temperature is 108.2 degrees Celsius. I'm sure I listed it correctly somewhere here. So let's go ahead and try this. All right. We'll do another example just in a little bit here. You can try this example. This one is correct. This one, you'll have to tell me what the right answer is. I forgot. You can try this out. Or if you want, there'll be similar questions in your Mastering Chemistry, okay? Jeez. Okay, so here we see a freezing point depression that I'm going to work out for you. So a chemist is trying to identify a human hormone that controls metabolism by determining its molar mass. And so then that molar mass would give him a great indicator of which hormone it is. Then he could look it up and maybe do one other test or two other tests to actually figure out finally which one it is. So a sample weighing 0.546 grams was dissolved in 15 grams of benzene. The freezing point depression was determined to be 0.240 degrees Celsius. And so again, we're going to do a very similar problem as we did before in that boiling point elevation for this. And so again, we look up the Kf for benzene. That's 5.12 degrees Celsius, kilograms per mole, which, by the way, if you look here at the Kfs, you can always get what you need for everything else. This right here is a temperature. This right here means it's going to have to be some sort of molality, right? Because molality is kilograms, moles relationship. So the molality for the hormone will be, we take the molality of the hormone is going to have to be the delta T that we were given divided by the Kf we were given. We're going to assume the hormone does not split apart in solution, which is a pretty safe assumption. It would be very, very bizarre and really a problem if this hormone was splitting apart in solution to make more than one particle. And so this should be one particle per mole, or 1 mole particles for every mole of hormone. And so we put in our numbers, we do the math, we get 4.69 times 10 to the negative 2 moles per kilogram, which is our molality. So the next thing we need to do is we're going to need our mass of our solvent in kilograms. That's why we had that weight given to us. So we can take our moles per kilogram of our hormone that we got, the molality. We can set it equal to the definition of molality, which is moles of the hormone, divided by our kilograms of benzene. We could then solve. Alternatively, we could just take that we have this moles of the hormone. We know molality, so we just take the molality here, moles per kilogram, and we multiply it by the kilograms of our benzene. So kilograms will cancel. Either way will give you the same answer, and that is 7.04 times 10 to the negative 4th moles. That's a great thing about math, is you can take any way you want as long as you follow the rules for math, and you'll get the same answer, right? You just need to follow the rules. So we had 0.546 grams of hormone dissolved. We have that many moles of hormone. It has to have that mass. And so to get the molar mass, we'll take our grams, we'll divide it by our moles, and that will give us our molar mass, which is going to be 776 grams per mole for this hormone. It's fairly heavy, but that's actually kind of normal for something that's as large as a hormone. So why does the addition of a solute to a solvent raise the boiling point of the solution? All right, and so these are our options. The temperature required to cause boiling must be great enough to boil not only the solvent, but also the solute. B, solute particles lower the solvent's vapor pressure, thus requiring higher temperatures to cause boiling. Or C, solute increases the volume of the solution, and an increase in volume requires an increase in the blah, blah, blah. Something completely wrong. Okay, so the correct answer is B, and that's because the solute particles lower the solvent's vapor pressure, just like we saw in Raoult's law, thus requiring a higher temperature to cause boiling. And yes, that is true. If we lower the vapor pressure, it takes a longer time, it's harder to reach the same vapor pressure as the atmospheric pressure, which is actually the definition of boiling. Another way of looking at this is that the solutes are going to cause it to be harder to break apart and form the gas. Every time you break apart, you're actually going to cause that to become more and more concentrated, and thus it is going to go against the normal enthalpy relationships that we saw before. There you go. It will also go against entropy if you're curious. but we haven't really gone really in depth into that. You probably remember entropy, but you may not remember where it comes from at this point. We will go into further depth on entropy, by the way. Not this chapter. Osmosis. Many of you have heard of probably learning through osmosis. Unfortunately, that does not work. So the flow of solvent into a solution through a semi-permeable membrane is going to be the definition of osmosis. The semi-permeable membrane, what that means is it's going to be, well, if you just look at the wording, it actually tells you. Semi meaning sometimes, permeable meaning it lets some of the stuff through, membrane, so it lets some things through and doesn't let others. This is going to permit a solvent, but not solute molecules to pass through. And that's just like the membranes on your cells, by the way. In fact, many times if you're going to use a semi-permeable membrane, the original membranes that you used were literally things like pig intestine. And you just clean it really well, and there you go. That's your semi-permeable membrane. Those are still sometimes used depending on the purpose of what's necessary. It's a great way to recycle stuff that wouldn't normally get used. But there's also various types of synthetic ones. Osmotic pressure. Well, this is going to be osmosis, right? It's osmotic, but it's going to be the pressure that's applied because of it. So this is going to be the result of increased hydrostatic pressure on the solution than on the pure solvent. One of the ways you can help yourself remember this is if you have a solvent, you have a pure solution, the water is going to rush towards the solvent. This is going to mean anything in the way is going to get pushed and have pressure applied to it. This is going to be caused by a difference in levels of the liquids at equilibrium. And so right here, this is actually the process of osmosis. Here we have a little container here, a flask that has our solution in it. This then has a membrane separating it from an outer beaker that has the pure solvent in it. So as we watch this across time, what we will see is the pure solution will slowly move through the membrane and it will go into this concentrated solution. It will cause this solution to become less concentrated. It will also cause the volume to go up. You see the volume's going up here. This will actually cause the osmotic pressure to increase. If you look here, they were equal here. Now this is going to be above this level. And so what that means is your osmotic pressure is increasing. The pressure pushing this way is going to increase. And so, finally, at equilibrium, you're going to have equal amounts coming in and out of the solvent. Your osmotic pressure is going to be right here, this difference at equilibrium between the pressure here and the pressure here. You can see that this water levels went way down, this went way up. There's actually quite a bit of pressure there. Okay, so preventing osmosis. How can we do the reverse? Well, obviously we could apply our own pressure to reverse osmosis. By the way, you may have heard of this. It's called reverse osmosis, and it's one of the ways you can desalinate water or purify water. That's probably where you've heard it from. So we apply the pressure to the solution right here. And so we're applying pressure. What this is going to do is if we have an equal amount to the osmotic pressure, this is going to stop osmosis. The minimum pressure that stops the osmosis is actually going to be the osmotic pressure of the solution. If we apply greater pressure, this will actually cause the water to separate out in the opposite direction. Typically, it's actually very energy intensive to do so. So what are some of the uses of osmotic pressure? So this can be used to characterize solutions. This can be used to determine molar masses, and small concentrations of solutes will produce a relatively large osmotic pressure. So we can use much smaller amounts than we would have to otherwise. All right, so this is the equation for osmotic pressure. So this is actually going to show you the dependence on osmotic pressure on the solution concentration. Right here, this is the gas law constant, just like you'd find anywhere else. This right here is your temperature in Kelvin. This is your molarity of the solution. And this symbol right here is osmotic pressure, and it's in atmospheres just like the pressure of the atmosphere around you is in. Just remember that that is one form of pressure, right? And that's what we're talking about, force over an area. Now, if you're maybe wondering what that symbol is, it's actually capital pi, uppercase pi. All right, so let's consider this following model of osmotic pressure right here. And so we have a pure solvent, and we have right here a solution. The water is going to be rushing towards the solution, causing its volume to increase, and the volume of the pure solvent to decrease. This difference in that force is going to be the osmotic pressure. So what if both sides contained different pure solvent, each which with a different vapor pressure? What would the system look like at equilibrium? Assume the different solvent molecules are able to pass through your membrane. So what you're looking at here, if you had different solvent molecules, then you would actually have to treat these as being solutes in each different system. So what you should see and what you're looking at was you would again have a rush back and forth. But this would be an equal amount, more or less. This would have some of this coming over here and some of this coming over here. And so you'd actually be making two solutions over here. You'd be making a solution which would have sort of a part of this side, part of this side solution, solvent, making this solution. You would also have the solution that would have three things in it. And so what you would expect is this would actually have a lower osmotic pressure right here. You would expect less of this. Okay, so determine the molar mass of a certain protein. 1 times 10 to the negative 3 grams of it was dissolved in enough water to make 1 milliliter of solution. The osmotic pressure of this solution was found to be 1.12 torr at 25 degrees Celsius. Calculate the molar mass of the protein. So we're going to use our equation that we looked at before right there. And we have these values. So we have a constant. We have 25 degrees, which will give us 298 Kelvin. So we can plug those in right away. We also have our pressure right here. And so that will be the next thing we need to calculate in. We need to put in is we then need to transform this pressure, this torrs, into atmospheres, which we see as the pressure that will be used in this equation. And again, how do you figure out what is the correct units? Look at your constants, okay? Always look at constants. Constants always have the units you need to use in the equation. That's it. By the way, I did almost my entire chemistry degree never remembering a single equation off the top of my head because I just used constants to deduce what they were. But I would not particularly recommend that. It's not easy to do. It takes a little bit of time. So note that the osmotic pressure must be converted to atmospheres. So we've converted that to atmospheres. If we then solve for M, which is our molarity, we're going to take our atmospheres that we just got, we'll divide it by R and T, and that will give us our molarity, which we find is 6.01 times 10 to the negative 5th moles per liter. There we go. So since 1.00 times 10 to the negative 3 grams of protein was dissolved in 1 milliliter of solution, the mass of the protein per liter of solution would have to be 1 gram per milliliter. Or 1 gram per liter of solution. We got our here concentration of our solution in moles per liter. And so we can then use these two concepts together that are both for 1 liter. And so what we see is that there are 6.01 times 10 to the negative 5th moles of the protein in that liter, and in that same liter there's a mass of 1 gram. And so to get our grams per mole, we'll take our mass of our grams right here, we'll divide it by our moles of our protein, and that will give us our grams per mole, which is a molar mass. So this molar mass is a fairly large number as far as you've probably ever seen, but it's actually extremely small for a protein. That would be actually somewhat unrealistically small for a protein. Typically, proteins are measured, the base unit for measuring proteins is thousands of grams per mole. So this is actually very small. All right, so what are some of the consequences of osmotic pressure? Well, you can use it for a variety of different applications, one of which is dialysis. So dialysis, this is actually going to occur at the walls of most animals and plant cells. The membranes are going to permit the transportation of or transfer of solvent molecules across the membrane. These small solute molecules and ions can also be transported across the membrane. Typically, there are specific channels that will allow that to happen, though. So the application is going to be the use of an artificial kidney, machines to purify blood. In an animal, this is going to happen at your kidney, and you will transfer these various different small solute molecules and excess solvent out. You will urinate it out, and you will get rid of the waste particles that you don't need. In an artificial dialysis, you will do this, you will do much the same thing, only you will use a membrane to separate the two in the dialysis machine. And so right here we have our impure blood, we put it in. You're going to have your waste products, which are going to dialyze out into our washing solution. And these are going to go through your membrane to be removed. And on the other side, you're then going to put your purified blood out. This is somewhat of an oversimplification. Understand that. If you want the full thing, we can always go to that in like biochemistry if you ever take it. Anyways, or in later classes, if you're going to go on for a medical degree, you'll get something. Typically, you'll start talking about biochemistry though. Okay, so one of the most important applications of osmotic pressure and osmosis is when we talk about isotonic, hypertonic, and hypotonic solutions. Isotonic solutions is going to be solutions with identical osmotic pressures. So, if you administer intravenously a fluid to a patient, it must be isotonic with the body fluids. If you do not have it isotonic with the body fluids, you will cause damage to that patient's cells, you can cause them great pain, and even kill them. Hypertonic solutions are going to have an osmotic pressure that is higher than the cell fluids. Hypotonic solutions are going to have an osmotic pressure lower than that of the cell fluids. One way to easily remember this is hyper as in greater, more. Hypo is less. So hypertonic, greater, hypotonic, less. All right, this is the important reason for hypertonic, hypotonic, and why you don't want them. So right here we see a normal RBC, or red blood cell, and this is in an isotonic solution. Looks good, it can flow around your blood carrying oxygen and various different types of nutrients, which isn't as normal actually. Most nutrients are not transported in red blood cells, but oxygen being the major one we're concerned with here. And it doesn't stick anywhere, it doesn't blow up. Cool, we're doing great, we're alive. If you introduce a solution which is then hypotonic, then what's going to happen is the water will flow out, and this is going to cause I got ahead of myself again. Jesus, I do this all the time. So when I do these, I sometimes have my notes here, and I skip lines. I don't pay attention to what I'm doing sometimes because I get tired, because it's quite a long time to talk and lecture in one sitting. And so, sorry, this is a hypertonic solution. This is where the osmotic pressure is greater outside the cell. This means a higher concentration, higher tonic concentration outside the cell. So what's going to happen is the water will flow outside of the cell. It will flow into the solution you introduced. This is going to cause the red blood cells to shrivel. And so this is smaller than this. It's hard to tell that, but it's shriveled. It has sort of edges, sharp edges. These actually can cause and collect in arteries. And so you can cause blockages. You'll also cause a very painful experience. This will also make the person feel very sick. And this is actually what happens when you drink salt water, if you're curious. Your stomach lining cells become shriveled. And that's because it is hypertonic. That's also what happens if you leave your hands in salt water. You'll see that same shriveling. And so, yes, that is harmful over the long term and will not, of course, help. This is why, for example, you cannot get water out of things like salt water. And actually, you don't get very hydrated if you drink soda, because those are all somewhat hypertonic to you. You don't actually gain water, you lose water to them. All right, so this right here is a hypotonic solution. And so what you're seeing here is this is a red blood cell normally. And in a hypotonic solution, that meaning hypotonic, meaning less concentration outside, the water will actually flow into the cells, swelling it. If it gets swollen enough, it will actually burst. And this is actually one way you can burst cells. Regularly, you'll see this done in labs where we'll take DI water and we'll put cells in them. And we'll literally just cause the cells to blow up, burst, so we can get the stuff out of them. However, you obviously do not want to do this in a patient, where if you put, instead of putting a properly calibrated bag or a dialysis machine, you instead will put, if you put DI water, for example, into their veins, you will cause their cells to burst in the veins. And this is called hemolysis. Hemo is in hemoglobin, as in the stuff in red blood cells. Lysis is in breaking. By the way, this is called crenation, when you shrivel the red blood cells. All right. Obviously, this is very painful. Hospitals regularly do this, actually. This is hopefully uncommon in that hospital, and it is overall uncommon, but it is something that does happen, and yes, causes many problems. So please know what that is, understand it, and do not do it. Okay, so consider a setup in which pure water is separated from an aqueous sugar solution by a semi-permeable membrane, which allows water to pass freely but not sugar. After some time passed, what will have happened to the concentration of your sugar solution? So what would you expect to happen here? Well, on one side you have your pure water, and the other side you have your sugar, right? And so you would expect your sugar solution to draw water over to it due to the osmotic pressure. And this water that's being drawn into it is going to increase its volume and cause it to have a lower concentration eventually when it's at equilibrium. And so, yes, you would expect the concentration to decrease. All right. So let's do another interactive example here. What concentration of sodium chloride in water is needed to produce an aqueous solution that's isotonic with blood? So what we're looking for is something with an osmotic pressure of 7.7 atmospheres at 25 degrees Celsius. The important part of here is the 7.7 atmospheres. That's what we're actually looking for. All right, so we can calculate the molarity of the solution from the following equation, of course, which is that same one we've been looking at before. And so again, look, we have our molarity. We get that to one side. We have our osmotic pressure. We divide it by a constant, which is R, and our temperature, which we had degrees Celsius before, so we can get our Kelvin. And so that 7.7 is on top. Then this is divided by the 0.08. That's the constant that you can get from your book or any other place. I even gave you a sheet that has that on it. And then this is 298 Kelvin on the bottom. Again, that is that 25 plus 273 as normal. And so this gives us a molarity of 0.315 moles per liter. And this is going to represent the total molarity of our solute particles, not the NaCl's, right? We have to account for, in this case, the fact that NaCl will give us 2 ions per our formula unit, and therefore it gives us 2 particles for every formula unit of NaCl. And so the concentration of the NaCl actually needs to be half of that. So it's 0.315 molarity divided by 2 to give us 0.158 molarity of NaCl solution. And that's what we're looking at right here. Alright, so reverse osmosis, this is going to result when a solution in contact with a pure solvent across a semi-permeable membrane is subjected to external pressure larger than the osmotic pressure. And so if you put enough external pressure on this, the pressure will cause a net flow of solvent from the solute to the from the solution to the solvent. It will flow from the higher concentration to the lower concentration under these high pressure conditions. The semi-permeable membrane will actually act as a molecular filter. Essentially, you're pushing the water through, which is small enough to go through the membrane, while the particles cannot go through. In fact, because most reverse osmosis is used in terms of something like salt water, the reason they can't go through is actually the charges on them, if you're curious. And the ions cannot go through because they're charged. So that will cause the solute particles to all build up on one side into a very high concentration solution. You can then collect that water, usually pure water, on the other side. This will help you remove solute particles from the solution. And this is what we're doing right here. This is reverse osmosis. We apply pressure greater than the osmotic pressure here and get our pure solvent out. This is an example of a reverse osmosis process, which is desalination. Remember, whenever you do reverse osmosis, you will never be able to get all the solute out. You will always have some of the original solution remaining. It will be lower volume, it will be more concentrated than the original solution. So what you're going to do is you would then have your salt water. It's pumped out and stored, so you don't have you have an uninterrupted supply of it. It also is filtered for large particles, so you don't have sand and stuff, small pieces of sand, that sort of stuff in it. This also gets rid of a lot of the bacteria and stuff too. So it's then going to go on to your plant, your desalination plant. This is going to be using reverse osmosis to undergo desalination. On one pipeline, you're going to dump the brine back into the ocean. This brine will have all those different salts and compounds that the original ocean water would have had. And it will have to be redissolved and go into equilibrium with the ocean again. This then is going to have your fresh water that you'll send on to your water supply. Why am I even bothering to mention this? You actually will probably have to have some sort of desalination that's occurring within the next 30 years. It's predicted within the next 10 years, most places will not be able to provide their own drinking water using the existing groundwater that's there. They'll have to depend on either other locations or desalination. Alright, so I've mentioned numerous times that certain compounds like salt water, salt, NaCl, this provides you more than one particle for every formula unit. And so this is actually what's referred to as the Van't Hoff factor, I. This is going to provide your relationship between your moles of your solute that are dissolved and the moles of the particles in solution. And so your Van't Hoff particle is just the number of particles for every formula unit of your solute, or the moles of the particles in solution per moles of solute dissolved. The expected value for I can be calculated for salt by just noting the number of ions per formula unit, and so salts are very, very easy to do. All right, now, ion pairing. Oppositely charged ions can aggregate and behave as a single particle. So, in a solution, a positively charged and negatively charged ion can come together and they can still stay dissolved in the solution. You haven't seen a huge number of these in lab. We haven't really talked a lot about it. This is where we're sort of introducing it. But you have seen a number of these actually in nature. This is, for example, how aluminum ends up being dissolved in lakes and causes a bunch of fish to die. So this can occur in solutions. This is showing you sodium and chloride ions in solutions. In this case, sodium chloride, actually this would eventually fall out of solution if they were to ion pair. There are ion pairs that can occur that will not fall out of solution. Copper does it quite a bit, and that's how you get different color solutions from copper. So this is essential in concentrated solutions. As the solution becomes more dilute, the ions spread apart more. This will lead to less ion pairing. So the more concentrated solution, the more it's going to occur. In all electrolyte solutions, this will occur to some extent. You will have ions pair, they will not drop out of solution right away, and they likely will split back apart and other ones will pair. It's just a small fraction of your ions will always be like this in pretty much every electrolyte solution. The more concentrated it is, the more likely it's to happen, and certain ions do this much better than others. The deviation of I from your expected value is the greatest when your ions will have multiple charges. So in NaCl, it's expected to be very, very low because they're both a plus and minus 1. The ion pairing is going to be very important for highly charged ions. So let's look at this. NaCl, you'd expect it to be very close to 2 particles. I is 2, NaCl. And your observed is very close to 2. Cool. Very, very similar. You don't get a lot of difference from the expected. MgCl2. Now, your Mg has a 2 plus charge. What this means is this is more charged. It's a stronger magnet. So it's going to be easier for this to cause ion pairing with one of the Cl's because it's a much stronger magnet. And we see that we have more deviation. Our observed I value is more deviated, more different than the expected 3. Here we see MgSO4. Again, we have the Mg2+, but we also have the SO4 2-. These are both stronger magnets, and so we get an even larger deviation. Right here we have FeCl3. The Fe has a 3+ charge. That's a very strong magnet. And so we see that we get a fairly large deviation from the expected 4 here. Again, HCl, these both have an H+, Cl-, their charges of 1, and so we get very little deviation because they don't have much charge on either. This right here is glucose. This is a non-electrolyte. It's just shown for comparison. We don't get any ion pairing here because there are no ions being split apart. And so we expect this to be 1 particle, and it is 1 particle. That's great. All right, now, this ion pairing in electrolyte solutions, this is going to affect our colligative properties. So our colligative properties are going to be given by including our Van't Hoff factor in the equations. So right here, this is for the freezing and boiling points. We can represent these with a single equation. And that is the change in temperature equals the Van't Hoff factor I times the molality times K, which is the constant. All right, so for osmotic pressure, it's going to be just the same. We again have osmotic pressure equals I times the molarity times R times T. There you go. Notice you literally just include I. The reason that you can just throw I in there like that, times I each time, is molality is moles on the top. I would actually be multiplied by the moles that are on top here, and so we can just leave it split out like that. It's good. No problem. All right. Okay. All right, so we're going to work on this interactive example here. Sorry if I'm a little cold coming back. I had a long pause I needed to take. Sometimes I get some long messages. Okay, so this is going to be an osmotic pressure problem again. In this case, we're going to have to use the Van 't Hoff factor, I. And so right here we have our osmotic pressure that we're trying to, the observed osmotic pressure for this solution right here, which is 0.1 molarity of this, that formula units, at 25 degrees Celsius is 10.8 atmospheres. So we have our pressure. We have, of course, right here, we have our pressure that's been observed. We're going to have to figure out and use our calculated pressure. We're going to have to use the formula to compare. And so you're going to want to get the expected and experimental values for our I to compare and see how close these values of I are for this formula. So one of the first things you might want to do is try figuring out your expected values for I. And in this case, because this is an ionic solid, you should just go ahead and count up your ions. And so you here, this is a little bit of a test on if you remember last semester. Right here you have iron, of course, that's one ion. Here you have what is called a polyatomic anion, NH4+, and you have two of those. And so there's two ions right here. These do not split up anymore. That is the ion right there, NH4. The SO4, of course, is another polyatomic anion. There are two of those. Those don't split up anymore. They are covalently bonded within the SO4s. All right, so we have 1, 3, 5 that we would expect. And so you would expect that to dissociate into 5 pieces and give you a Van 't Hoff factor of 5. So the next thing we're going to do is we're going to use our equation and we're going to calculate it for our Van 't Hoff factor in this case. So we're going to take our equation, we're going to solve it for I, and that's what this is right here. We're going to plug our experimental value in, which is 10.8. M is this value right here, 0.1, right there. R is, of course, the constant, R. We had 25 degrees Celsius, so that's 298 Kelvin. That'll go in for the temperature. So we go ahead and plug these values in, substitute them in. We solve, and we find our Van 't Hoff factor for the experimental is 4.4. So the experimental here is less than the expected value. And we would presume this is because of ion pairing. Actually, there are other things it could be, but ion pairing would be a good guess for this one. All right, so as the concentration of NaCl solution increases, ion pairing would be expected to what? So if you have more ions in closer proximity, you would expect the ion pairing to increase. They'll bump into each other more often, spend more time paired up. Which of the following 0.05 molality solutions is expected to exhibit the greatest ion pairing? And so what you're looking for here is the strongest magnet. The strongest magnet is going to have the highest charge. And so iron chloride, that is an Fe3+, that will have a 3+ charge to counterbalance the negative charges on each of these chlorines, or chlorides in this case. Alright, now the next thing we're going to go into is the Tyndall effect. You've all seen the Tyndall effect, but you did not realize you were seeing it. So this is actually going to be scattering of light by particles in your solutions. This is used to distinguish between a suspension and a true solution. A true solution will not fall out of the solution as time progresses. It will stay dissolved. I've seen solutions that are 30, 40 years old that somebody in the lab had made and left there. A suspension will slowly settle out of solution. The perfect way of thinking about these, solution versus suspension, is this is like milk versus soda. Okay, a true solution, that's soda. That's the particles will stay in there even if it gets flat. You'll still have all the sugar in there. You'll still have all of these flavorings, all that stuff. It won't have a solid that collects at the bottom. Whereas a suspension is milk. Milk, if you leave your milk in there, you'll notice that particles start settling onto the bottom, and that's because those are actually suspension. They're not dissolved in there. The protein complexes and fat complexes are not dissolved in it. They're actually suspended in there. They're floating around much like a snow globe does after you shake it. And so after a period of time, the suspension will settle out. So when you have two things and you don't have time to let them sit there for days, or even weeks or months, because some suspensions will stay suspended for a very long time, what you need to do is you take a beam of intense light, you project that beam. The beam will be visible from the side in a suspension. So when it hits the suspended particles, they're so large, they'll scatter the light. And it will make it look like there's a light coming out from the center of the suspension. And when the light beam is invisible from the sides, that's a true solution. And that's because you don't have large particles in the solution causing the light to scatter. Instead, you just have particles in the solution that the light will be able to penetrate past, just like it does the water. Now, it may cause the light to change colors. That's fine. That has nothing to do with this, okay? That's actually the light frequencies that the solution absorbs. And so right here we see a great example. We have a laser pointer right here. This right here is a true solution. This right here is the suspension. You can very clearly and easily see it. You see that this actually passes through with a little bit of reflection off the sides of the glass. This one right here, it's scattering from the suspended particles right there. And if you take soap solution, you can do this at your house. You can take some sugar or salt, dissolve it in water and put it, then take soap and dissolve it in water. Do a decent amount of soap, so it's actually soap water. And then go ahead and shine a light through it. And you'll see this will just shine right through. This one, it'll have what's called a light bloom. Okay, so colloid dispersion or colloids. Suspensions of tiny particles in some medium can either be single large molecules or they can be aggregates of molecules or ions which will range in size from 1 to 1,000 nanometers. These are classified according to the states of the dispersed phase and the dispersing medium. So right here we see various types of colloids that you actually probably know all of and have seen before. For example, this is fog. That is a dispersing medium of gas, which is the air, and a dispersed substance, usually water, which is your liquid. And that is a type of aerosol. Aerosol sprays are, of course, aerosols as well, and they are another example of this. Smoke is going to be a air, gas, as your dispersing medium, and then solid soup particles being suspended in it. And that is another type of aerosol, by the way. Airborne bacteria and viruses are another example of this. They are another type of aerosol. Like the COVID-19 virus is a solid virus suspended in air, which is, again, an aerosol. Whipped cream, soap suds, these are both examples of a dispersing medium, which is a liquid with gas dispersed throughout it. That's what makes whipped cream so light and fluffy. And this is called a foam. Milk and mayonnaise are going to be a liquid dispersed in a liquid. And so you have water, which is the dispersing medium. Your dispersed substance are typically fats, and this gives you your emulsion. Paints, clays, gelatins, these are all solids dispersed in liquid water usually, though you can have paints that have oil paints, of course, where this is oil. This is called a sol for the colloid type. Marshmallow and polystyrene foam, don't get confused when you try to eat one, is going to be a solid with a gas dispersed throughout. And that's why you see those little pockets of gas if you look very closely. In styrofoam, you can actually see the little pockets if you look really close. And these are called solid foams. The pockets of gas is what makes the marshmallow so light and fluffy. Butter and cheese, these are actually going to be liquids that are then dispersed through a solid. The thing that's being dispersed for butter and cheese are usually various types of proteins, sugars, etc. The solid is usually a type of oil in these cases. The solid emulsion is what those are called. Notice it's like an emulsion, but it's solid. Ruby glass is actually a solid dispersed through another solid. The glass being the solid is dispersed through. And this is called a solid sol. Stabilizing colloids. So the major factor here is electrostatic repulsions in these. So a colloid is going to be electrically neutral. And that means that they don't repulse or attract each other en masse. Most solutions in bulk, you typically have to have overall neutral conditions. Having overall positive or negative conditions will cause a flow of electrons towards or away from it, which is what we call lightning. So each particle in the center is going to be surrounded by a layer of positive ions. These will have negative ions in the outer layer around those. When placed in an electric field, the center attracts from the medium a layer of ions, all the same charge. So the outer layer contains ions with the same charge that repel each other, and so the colloids do not stick together and they stay apart so they do not fall out of solution as easily. Coagulation, this is going to be the destruction of a colloid. Typically the easiest way to destroy colloids and cause them to fall apart from solution is heating. So heating is going to increase the velocities of the particles. This will cause them colloids to collide. When these colloids collide, if you can overcome these repulsions, these will stick to each other, creating a larger colloid, which will be too heavy and will fall out of solution. So if you have enough energy behind the collisions, you can penetrate the ion barriers and the particles can aggregate. The repetition of this process will enable the particles to settle into another layer, which will no longer be suspended. Another way of doing this is to add electrolyte that will neutralize the absorbed ion layers and thus strip the colloids of these ion layers, allowing them to aggregate and fall out of solution easier. And so the two ways you have probably heard of and seen to create things like mayonnaise and stuff, if you didn't know, cheese, mayonnaise, these are all created from usually milk. And you can take milk. If you heat milk up, you'll see the cheese curds, if you will, start falling out of the solution. You're causing aggregation, like so, like we just talked about. The other way you can, of course, make cheese or mayonnaise is you can put an acid in it. An acid is a type of electrolyte. It'll neutralize the absorbed ion layers and therefore cause aggregation again. By the way, you can do sort of a funny thing to people. If you get people to drink cream or milk and drink a orange juice or lemon juice at the same time, it'll puff their mouth full of a aggregated colloid. And it's kind of amusing because it usually causes them to spray it out because it tastes kind of weird. Anyways, some of the examples of coagulation are going to be, of course, colloid clay particles in seawater coagulation. which is due to the high salt content. This is why whenever you see a basin or a bay where the river empties out into the ocean, you'll see it collect up silt in these sort of formations of these colloid clay particles coagulating out, creating these sort of silt formations, if you will. And you usually have to clear those out every now and then. And that's why bays need maintenance, so people can, sail in them and stuff. Some of the removal of soot from smoke. So suspended particles are removed when smoke is passed through an electrostatic precipitator. You guys are probably most familiar with this as an air purifier. There's a number of air purifiers that use this phenomenon to purify particles from the air, and that's what they're taking they're using coagulation due to the electrostatic attractions. Okay, folks, good job. You take care. Have a great day. Let me know if you have any questions or issues.